everybody okay. It should be. C'è qualcuno c'è qualcuno che si interessa a questo? Can you send a message to Roy Kerr, please, to connect as soon as possible by mail? Okay, we will try to get him. His time delay and so forth, but we arrange that, and I hope everything will be okay. Chairman, we can start.
We can start, okay. Good morning from my side as well. Before we start, I have been asked to give you an announcement by the organizers. There will be a group photo of all of us, and this will be outside in the coffee break. Before you go for coffee, please go outside, wait for the announcements of the photographer, please. We will see. This is not my organization, okay?
Well, everybody here, you were not, because I'm afraid that it was not strong.
Yeah, okay.
Loud enough. Hello. Is everybody heard the announcement? Was it possible to hear about the photo afterwards? Okay.
Yeah.
Yes, because I thought that it is that sound was not good enough for all ears here. Yes.
We announce it later again. We announce it later again.
No, it's enough.
Yeah. Okay.
This is good microphone.
Give it to Remo.
Okay. Oh, it's
So,
the best.
Close, yeah. Okay. And we have Roy Kerr with us.
Okay, we can.
Oh, we go on. Okay.
We go on.
This morning we start with the presentation by Dee Lee, but before this will happen, Remo asked for the ceremony for the giving him the award.
We were hoping to coordinate with Roy, because traditionally he has always been the person in the last 20 or 30 years to deliver the statue to the person who receives. And just to make clear, this is the object. Excuse me, sir, I'm speaking, okay? You understand? I'm speaking. This is the object. It came from an undergraduate student at Princeton, who I asked him one day to plot the trajectory of particles around a Kerr black hole. Mark Johnston was the name. He became famous later, not for this computation, but he was working with Riccardo Giacconi on the X-ray and so forth. But the first trajectory was so interesting that I decided to do three-dimensional. And then the idea came to ask an artist to reproduce. And we had a big battle. Everybody is late this morning. Well, some are still here. And start a big battle between me and my wife. Because my wife She will be, she told me she will be here today. Because she is an art historian. And I showed to the artist the object. And he did his own interpretation. Was terrible. Was like here, I mean, was terrible. And then I said, look, if you want to do this statue, we give you the coordinate, but you cannot change even a millimeter from the value which we give you. And my wife became cautious. She said, you cannot do that to an artist. He has the freedom to interpret. Well, I said, yes, he has the freedom to interpret if he wants to make in gold, in iron, in plastic, but he has no other freedom because the object must reproduce Einstein equations attentively, because otherwise it's not fair. Well, we discussed fiercely, but the artists start to do this, like I said. But my wife was not convinced. Yes. And of course it's new because it's not a statue. Usually an artist makes a statue of a person. There are the feet, the head. That is a statue. But this is not on the earth. It's around a black hole. And therefore there is something new. That is this the statue? Or is this the statue? Or is this the statue? They are all valid. They're all valid, but there is no a statue on the feet and the head. No matter how you look, it's a realization of the statue. But then she was not yet convinced. And then I said, well, we will go on anyway. No. Fortunately, there was an old professor at the University of Rome who was very famous and was still active. And said, okay, let's go and ask him. And we put that in a box. We went to this very, very famous professor. And the professor said, okay, you give your speech, and then your wife will give her speech. And then we will decide. Okay, I did the speech. The same as I did today. My wife did a speech that the artist cannot be enforced to respect the Einstein equation. And then the professor said, let's look at the statue. And we opened, like today, the box. And then, like Solomon said, it's beautiful. Therefore, it's art. And that was the end of the story. Therefore, keep in mind, when you will have at your home, that this object can be seen like that, can be seen like that. No matter the way you put, is still test. And as the famous professor said, is beautiful. Therefore, is art, although it fulfills the Einstein equation very rigorously. This object has been, you have the booklet where they are represented all the, you have the booklet? Where, yes, it's inside there. Here it is. Where they are, every one of us has a copy of the booklet. Here they are, the first equation, the equations which we integrated. The equation we integrated, you have the booklet in your bag. These are the equations, these are trajectories, this is a picture, and so forth. And this is the presentation by my wife of the statue, of the text. Okay. Here. And then here you find every one of you has a copy, the previous people who received. Many. And every Grossman meeting, we give 3. Sometimes 4, but in general 3. And this year we will give 3. Therefore, I did enough. And let's proceed to the first one. And it is a pleasure, like the booklet say. Where is the booklet? There. The first one go to Professor Dilly. And it is a pleasure to give him. And I will Dilly to say a few words by receiving the award. It's a different realization. No matter how you look is valid. In fact, somebody found a way to put in something which rotates, and you can see a different moment. It's up to you now how to do that.
Yeah. Well, thank you very much, Remo, and the organizing committee. This is truly an honor. So thank you.
And the motivation reads, for his groundbreaking contribution to the scientific definition of the most sensitive radio telescope and his numerous innovations in characterizing the dynamic of the universe, resulting in precise measurement of the interstellar magnetic field and advancing the field of fast radio burst into a high statistics era. This is the motivation. Up to you now.
Right. Thank you. Get my clicker.
There is no better introduction for our first speaker. Please take over and talk about.
Thank you. Right, I'm truly honored to have this opportunity to report some of the progress, particularly from the FAST telescope. So here is our instrument. You can see that spiral of light. So that actually a truck that was being driven underneath. So you can see the light shining through the instrument. So it's not a solid panel. In reality, more than 50% of this huge area you are seeing is made up of holes, but those holes are small enough. It's about half a centimeter, that much less than the operating wavelengths. So it still functions as an effective reflector. The volume of this dish with a diameter of 500 meters can, if you fill it with wine, every person in the room, in fact, every person in the world will get at least one bottle and probably two. So, and at the moment, the current frontier, I dub it sort of the time frontier that we are exploring. Right, so I'm again excited, honored to be in the home country of Galileo, who with his first usage of telescope toward the sky and the thinking about physical foundations that underlying this universe, actually initiate both modern astronomy and modern physics. Is one person, so he has many achievements, and I think throughout his achievement, there's the audacity that shines through. And this joint thinking about sort of celestial and cosmic object with the physical foundation culminated in two papers, Planck 1900A and Planck 1900B. There, he actually tried to fit the black body radiation. And what's more perfect black body than a star, right? Which can be characterized by a single temperature. So there he has this great insight that in order to solve the so-called ultraviolet catastrophe, you only need to demand there's a minimum unit of energy, or actually is the number that try to characterize all the spring that he has threaded out that adiabatic system. So this actually brings the physics in the 20th century into the quantum era. And further on into the 20th century, I found this great article, very brief, that in memory of Fritz Zwicky, the pioneer in optical surveys. So this is my Freeman Dyson, published in 2005. The first sentence read, the first person to carry out a modern survey of the night sky, Fritz Zwicky's astronomical observations led to a new picture of a turbulent universe that's punctuated by violent events. So that dynamic universe, quote unquote, really shining through to humans through optical surveys. But currently, the sort of most mysterious and unexplained discovery lying in the radio band. That's in 2007, particularly from Duncan Lorimer, Matthew Bills, and Maura McLaughlin. They found the first so-called fast radio burst. That's that signal that is unrepeatable. And unfortunately, it also looks similar to some of signal come from microwaves. So at the time, really, it's a novelty, but not many colleagues believe in its robustness. But it's curious to note that the last sentence of the summary paragraph of the discovery article read that hundreds of similar events could occur every day. Keep in mind, at the time, it's only one event that even not too believable. And then in 2013, in the second discovery article that really give the name to this class of phenomenon, fast radio bursts, the last sentence of the abstract read that the study of such object could help determine the baryonic content of the universe, which is very quickly borne out in this landmark article from J.P. McCord, the so-called McCord relation. Now with independent measured redshift and the so-called dispersion measure, the authors claim that already solved the missing baryon problem. So about 40% of the baryon should be situated in the intergalactic warm electrons. So this is a field that is quickly growing. And to explore the radio band for about half a century at the apex of collecting area is the undoubtedly the Arecibo telescope, which discovered the double neutron star that propelled the Nobel Prize in Physics in 1993. And one of the landmark of the fast radio burst field is happened in between 2015 and 2017. The Arecibo telescope discovered the first repeating fast radio burst. Then you can use all your astronomers' tools toward this object. So for the first time, we can measure its host galaxy and now can backtrack to derive its intrinsic energy. So it turns out concentrated in this one pulse, this is just one of the representative pulses, lasts a few milliseconds. There's enough energy equivalent to a full year worth of solar radiation, which since we only get a tiny fraction of the solar radiation from the sun, since we are a vast distance from the sun, this intrinsic energy could power the current global society for about 1 trillion years. Some of the more smarter mind in the room could help check my quick estimate. So I think it's fair to say that it's still not coherently or reasonably explained how we generate such energy in the natural world. So Arecibo telescope, unfortunately, collapsed toward the end of 2020. So since year 2020, the so-called China Sky Eye, the 500-meter aperture spherical radio telescope, has been carry on and forward Arecibo's legacy. So it's largely motivated by Arecibo concept, but outfitted with modern technology. For example, this active surface. So we drive this vast surface area through 4,500 active panels to reform it from part of a spherical cap into a parabolic shape to focus the parallel wave come from celestial object. And at the moment, it's still the most sensitive radio detector. We are anxiously waiting for the square kilometer array. So since 2020, we have also implemented a slew of novel technologies. One of them is so-called high cadence Cal injection technique, which help us realize the first commensal large-scale survey of pulsar search, H1 imaging, galaxy search, and transient, particularly fast radio burst search. So this is dubbed the so-called commensal radio astronomy fast survey, or CRAFS, the first of its kind. Here is a short promotional video. So we have 6 towers, and we change the shape of the telescope, then just fix it on the sky and let the Earth rotate to drag our beam across the sky. And the advantage of radio detectors is that we sample the full field in time. So you only need to sample it once and process it into different data streams for different scientific objectives. So with a large collecting area and fast time sampling is particularly suited for transient phenomena. So the 6 towers host both the cables, power cord, and optical fibers. So it can transmit power and signal. That's our great expectation, but it's still about 10 years away. So we are right now about 20% into the design crafts survey. So this is to the scale. On the left, the Arecibo, the Great Arecibo Telescope. On the right is our FAST telescope. So back in 2003, Paul Goldsmith, the Arecibo director at the time, and I published this little observing technique, so-called H1 narrow self-absorption. And our real motivation is to utilize the Zeeman effect of so-called Hinsa to measure the interstellar magnetic field. But it takes us 2 decades, and it finally got realized in a paper led by Tao Chong-Ching, that we utilize the unparalleled sensitivity and the really, really clean optics of the FAST telescope to get this first Zeeman measurement with my Hinsa technique. This was published at the beginning of 2022. It corresponds to about 4 microgauss, which is only about 1 in 100,000 of the Earth's magnetic field strength, and much lower than the canonical star formation or ISM evolutionary picture. So it potentially revolutionary. This is a single measurement. So we are strive really hard to see whether we can apply it systematically to the interstellar medium. So since early 2020, in about 4 years of operation, right now FAST is carrying out more than 400 projects with scientists from more than 30 countries, generate hundreds of journal publications, including 9 on Nature, 2 on Science, particularly in pulsar discoveries, high quality H1 imaging, magnetic field strength measurement, but the vast majority of the quote unquote high impact publication come from the study of fast radio bursts. So here this is a plot that always outdated since particularly Professor Caspe's CHIME instrument keep generating new discoveries. So you can see this white dot, the number of discoveries is certainly dominated by CHIME, for which we are really grateful. And so the x-axis, I put on the estimated cosmic age. If we treat the universe at age 0 and Big Bang, and currently say it's about middle age, then you can roughly separate it out into age groups. And the vertical axis is the estimated intrinsic energy or brightness in the unit of solar radiation. So those weak bursts can be equivalent to a few minutes of solar radiation, but those very bright ones can be worth of decades of solar radiation. And if such bursts exist at the beginning of the universe, it can be seen out to redshift of 10. And at the moment, we have no reason to believe that they don't exist because we know that there are black holes and compact stars there. Yeah. So the based on the fast discoveries, we estimated that every day on Earth, there are more than 120,000 fast radio bursts detectable for the full sky. Let me repeat that number. So 120,000. There's 24 hours in the day, 3,600 seconds in an hour. So that's about 80-some thousand seconds. So we are truly living in this turbulent universe that's punctuated by violent event, as stated by Freeman Dyson. So it is up to us astronomers and physicists to really understand this explosions. And we also find a very active and so-called persistent repeaters, so-called 190520. So it has a counterpart, so-called persistent radio source counterpart. So when most of the source, it will burst, then disappear. Some give out repeated bursts. And this source not only give out repeated bursts, but when it's not bursting, there's also a light bulb that keep generating flux. So it looked really like a super bright supernova remnant. And both 121102, the first known repeater, and 190520, situated on the peripheral of a metal poor galaxy, I think it's not by accident, but it's still small number statistics. And one of the weird characteristic is that more than 80% of the dispersion measure, or the sort of the plasma that the signal transmits through, has been confirmed to come from near the source. So that raises challenge regarding using the dispersion measure, or the so-called McCord relation, to measure the cosmic matter. But it's also a opportunity or promise. If we have large number of statistics, we may be able to systematically correct such deviations. And I believe that we heard this wonderful talk by Wendy Freeman last night. So the goal is to get to 1% accuracy of Hubble constant measurement. And this year, there's the publication utilizing fast radio bursts claim to 5% accuracy. It's just a matter of numbers. With such abundance of fast radio bursts expected, I think we are going to get to 1% in about 5 years. And the 190520 is also the first source that we see the magnetic field orientation changes flipped on 2 to 3 months time scale. So that very suggestive of a bursting source, which may be a magnetar revolving around some stable, strong magnetized source. So it could either be a black hole or a massive star. So this is just a classical Chinese painting representation. You can see the orientation of the magnetic field and correspond to some orbit. The dragon is supposed to be the magnetar going around the black hole. Don't challenge me on the scientific accuracy of the plot. So after the discovery of 190520 in 2019, we are also fortunate to detect a very active episode from the first known repeater, the 121102, with more than 1,600 bursts. So here is a real burst, a real train of bursts represented on this famous Chinese painting from the Song Dynasty, so-called Endless Rivers and Mountains. So this set, published toward the end of 2021, the number of bursts supersede all the previous publications in this field combined, and it's come from a single source. So really provide us for the first time a comprehensive view of its energy spectrum, because the previous data set only covered this part. So your first intuition is to fit a power law, which is always a good starting point. But now we have to describe it with a bimodal distribution. At the lower energy end, we can fit a log normal distribution, which usually corresponds to some underlying stochastic event. At the high energy end, I fit a Lorentz-Cauchy function, which can be reproduced by the ratio between two independently distributed Gaussian variables. So it may be two coincidentally correlated random events. So we're still some distance away from the real origin, but we try to characterize it in some fundamental way. So here we put two series of events on the left. is the fast radio burst. On the right is earthquake. So the x-axis is so-called waiting time. So the time elapsed between each subsequent event. Vertical axis is the energy differential, the change of energy. So you can see on the left and on the right, they are both pretty messy, but they are messy in different ways. On the left, it keeps more or less symmetric, which means the elapsed time has no dependence on its energy differential. On the right, however, when you have a major event, which means one event shoots up, you tend to have the event goes left. So that's a well-known effect. When you have a merger earthquake, like the one, for example, in Chile, you trigger a lot of aftershocks. And such effect was not seen in fast radio bursts. So they are random in different ways. In fact, we can try to quantify their randomness and level of chaos by this so-called Pincus-Lyapunov diagram. So both are well-known mathematical physical tools, but for the first time, we sort of put them together. So on the right diagram, the randomness goes higher toward the right, the level of chaos goes higher toward the up. Then we can put a series of transient events, and the bottom line is the fast radio bursts are more random but less chaotic than solar bursts and earthquakes. And you can picture, for example, the random walk of Brownian motion, but the Brownian motion, the classical way, is happening on the spatial domain. We just put it on energy and time domain, so it looks like a random walk on this ET space. So this is a recent published article led by a student in my observatory. So this is just one of the work of trying to get the regularity of the time sequence from fast radio bursts. Although we don't know the exact celestial object that generate fast radio bursts, but the general consensus is it should come from compact object, because we usually need strong magnetic field to generate strong coherent radio emission. So the leading candidate is certainly the magnetars, but it could also be some other neutron stars or even involve black holes. And it's very hard in the universe to make a static black hole, right, that just sit there. It has to spin. So it's really become a systematic challenge now that with a large number of events that we just cannot find a single short term, so seconds or below periodicity, or even quasi-periodicity. So that I think it's become more and more a glaring challenge. Meanwhile, on the energy and time domain, it does look like a Brownian motion. And I think this way of analyze so-called PL diagram can be also useful for treating such times varying sequence. So although they are pretty random or mysterious, there are some regularity that threading through the fast radio burst event. So this is one of them. In the study, utilize both fast GBT and a slew of other instruments. We find that you generally tend to measure a higher percentage of polarization toward a higher frequency. And in fact, they can be well described by this single formula through the well-known so-called multipass scattering picture. And there's only a single physical parameter to be fit, so-called sigma Rm, which reflects the standard deviation of the plasma that this signal travels through. So the higher the sigma Rm, the more complex its environment or its magnetized plasma environment. And also, I think it's by no accident that the two sources with non-compact persistent radio source and very active that has the highest sigma Rm. So here is my unconfirmed, very hypothetical picture of the evolution of fast radio burst. I think the fast radio burst source was made out of some extreme explosion. You need that explosion to ionize the environment to give you this persistent radio source counterpart, which generate one or a slew of compact objects. They may be revolving around each other, and there's some mechanism to smear out its regular periodicity, or itself is very unstable. So at the start, it's generate this random time sequence of bursts, and the bursts shining through the plasma to get depolarized. And there's also some other effects that are being studied. But this phase will fade very quickly, like a supernova. It will fade in 1,000 to 10,000 years. And now you get a clean burst source with more regular polarization characteristics. And meanwhile, the source will become less active, and it drops from a very active repeater to a not so active repeater, or even a single burst in any of the regular surveys. I hope this has some promise, this evolutionary picture, to explain the majority of the bursts detected, if not all. So right now, the current field is still in its early discovery phase. So CHIME is certainly the major instrument in discovering the number of fast radio bursts. Fast is about 20 times more sensitive, but the detection rate is only about 1/100th of CHIME. That's limited by the field of view. I mean, we are single dish. It's very large, so we're looking at a tiny area of the sky. And if we put some thought into the development of modern astronomy ever since 1609, Galileo's first usage of telescope, its main function is to focus the light. But you actually don't need a mirror to focus the light, because if you can sense the phase front completely, you just need calculation. So that's and in the radio band, we happen to sample the phase front completely anyway. So what we need to do is to spread on the ground densely the radio antennas or radio probe. And the real constraint is that the distance between each probe has to be equal or less than half of the wavelength. So that requires a lot of metal and even more calculation. So here is on paper, a very quick estimate. So with only a single meter of collecting area, but with hundreds of probes, our yearly detection rate is expected to supersede a single dish concept by about 20 to 30 times. And hopefully in 10 years, when we can build up to 100 such units, we can supersede CHIME by about 20 times. So that's just the quantity of field that we can calculate. So here is another promotional video. This so-called cosmic antennae concept has already been built. We hope to get the first data stream by the end of this year. This is my last slide. So we're fortunate that to live in an era that we can still generate new discoveries, and the new discoveries propel us to think about their origin. And hopefully, in the near future, we can start to think about the underlying physical principle and to push our understanding towards so-called time frontier. So thank you.
Thank you very much. Stay with us. So are there at least one or two questions that we can accept maybe? Is there any comment? There is one. Maybe take a microphone. Take mine.
So I was surprised to hear that there are no periodic FRBs, but I did see papers claiming periodic bursts. Is that like?
Right, so there are two that are currently known. One is a 17-day periodicity, another is 160 days. So those are more on the orbital time scale. But there are certainly, we have ruled out for every active repeaters that we have enough sufficient sampling on the second to or sub-second level, the sort of spin periodicities.
Thank you very much.
Thank you.
Time is running down, unfortunately, but I think there will be time to discuss with you later. Okay, thank you very much. And I hand over to Remo again for next laureate.
Arriving, I did not put my jacket, but the solemnity of this presentation by Dili convinced me to put the jacket on for this even a posteriori. And we are fortunate that the mayor of Pescara just came in, and he will work with me to give the next award to Vicky Caspi. Please come in. Well, Vicky has been participating very effectively in this it's okay. Of the same topic of fast radio burst from Canada and from many institutions in Canada. And she's the head of the CHIME. How you spell exactly? CHIME? Chime? Chime. And for the innovative detection and comprehensive analysis of a large population of first radio bursts, significantly increasing their statistics, including repeating sources, which have boosted our understanding of their origin and their application in mapping the universe structure and composition. But when I first, let me still add one word. When I first decided to give the award to this topic, I sensed that this could become as exciting as now we are seeing. But the conviction starts to happen when they start to detect signal at z=1. This meant that it's not in the kitchen, but it arrives z=1 already. But I am very egotistic because I think you are seeing, I'm confident that you are seeing a gamma ray burst, which come even at z=10. Now we know z=9. Therefore, in due time, if the process keeps going and you enlarge this fantastic adventure all over the planet to observe, we will reach the equal 9 and test if that is the case. But anyway, this is a dream. This now is a reality. And I ask the mayor to handle this prize to you. Okay. To you.
Thank you very, very much.
We leave it here.
Okay. Thank you so much. Faster. Okay. Thank you very, very much. It's a tremendous honor to be here and accept this award on behalf of the Chime Fast Radio Burst collaboration. And I'd just like to acknowledge that one of my colleagues, Professor Juan Miña-Parra from University of Toronto, is in the audience, and I'd like just to have him stand up as well. Where did Juan go? There's Juan. And Juan is one of the leaders in our collaboration, and he will be giving another talk in the parallel session on fast radio bursts, I believe, on Thursday. Does this is not advancing? Ah, thank you. I had it. Great, perfect. Okay, thank you so much. And it's really wonderful to give this talk right after Professor D. Lee's talk on fast radio bursts, because he introduced the subject to you. I'll just remind you of a few key points. That fast radio bursts are few millisecond bursts of radio waves. Some are even shorter than that. Sometimes we see tens of microsecond duration bursts. This is a new field, as Professor Lee emphasized. In 2017, we only knew about 24 of these objects. And yet we knew then this is not an anomaly. This is not a rare occurrence. This is ubiquitous in the universe, with the inferred sky rate already recognized to be at least 1,000 per sky per day above typical radio telescope sensitivities. Most of these bursts have just a single peak. So you see one peak and then it goes away. Some are scatter broadened, as the one in the picture that you see here. You can see this is a typical fast radio burst that is a broadband. You see it from the pointer, I guess, doesn't work. There we go. Oh, it's up there. Okay. From the y-axis is radio frequency. So you see it arrives first at the high radio frequency and sweeps through the band. That's due to the dispersion measure, that is the integrated plasma column between us and the source, that gives us the hint that these objects are at cosmological distances, because the amount of plasma that we see that accounts for this long sweep is much greater than can be explained from anything in our galaxy. And you see that by scatter broadening, what I mean is that at high radio frequencies, the pulse is narrow, as you can see. And as you go to lower radio frequencies, the pulse broadens. This has to do with turbulence in the plasma that causes the dispersion. Radio waves that would be scattered away from the line of sight get scattered back to your line of sight. That causes an extra delay and a broadening of the pulse. Sometimes we see pulses, and I will show you examples of this, that are multi-peaked. Especially, as I'll explain, the repeating fast radio bursts love to produce multi-peaked bursts. We don't know why. Once we acknowledge that these are at cosmological distances, we can estimate the energies of detected sources, that typically between 10 to the 35 and 10 to the 43 ergs. So although these are not comparable energetically to gamma ray bursts, this is radio after all, Still, for radio sources, these are among the these are the most luminous radio transients we know of, certainly by far. And very importantly, while most of them, once you see one burst, it disappears, you never see it again. Occasionally, some of them repeat. Some of them come back and you see them many times. So repetition, some repeat and some don't. What does this mean? Could it mean that there's different classes of fast radio bursts? Or can it mean some are cataclysmic? You see just once they explode like a supernova, never to come back, and others are rotating neutron stars, perhaps something very compact because it has to last only a millisecond. For the repeaters, the typical models that are discussed in the literature are that some are radio pulsars like the Crab pulsar, but this is possible, but it's energetically very challenging. We know the Crab pulsar, the most luminous pulsar we know of in our galaxy, the luminosity is comparable to low luminosity fast radio bursts, but we know from radio pulsars in the galaxy, the radio efficiency is typically very low. It's very hard to explain how you can get the sorts of energetics that we see in fast radio bursts from Crab-like radio pulsars. Perhaps it's a magnetar giant flare like the cartoon is showing, and I'll show you almost certainly some of the fast radio bursts are due to magnetars, but the phenomenology of fast radio burst in general is unusual for magnetars. It's a little hard to explain all of them being magnetars, so that's not impossible. They're found, in some cases, we can localize them on the sky sufficiently well to unambiguously identify the host galaxy of the source. You can see here the ASCAP telescope in Australia has been the leader in this field, and you can see the circles are the uncertainty regions. In some cases, we find them in the spiral arms of spiral galaxies. Occasionally, we find them offset from the optical region of the galaxy. Typically, they're in galaxies that are forming stars, but not always. We've sometimes found them in dwarf galaxies. There's a whole variety of types of galaxies we've found them in, and this is early times. We're still trying to understand this as quite a diversity. But even if you don't care what FRBs are they young in star-forming galaxies? Are they old in quiescent galaxies? Even if you don't care if there's many different classes of repeaters, even if none of that's important to you, what is certainly true is that fast radio bursts represent a novel new probe of the structure of the galaxy, because we detect their dispersion measures, that is the integrated plasma column, and when we can identify a host galaxy unambiguously, we know the source is redshift. And so this is the now famous Macquart plot, where you can see on the x-axis is the redshift of the host galaxy, and the y-axis is the dispersion measure after removing the plasma, subtracting off the component of the dispersion measure due to our own galaxy and its halo, and due perhaps to some plasma in the host galaxy of the fast radio burst, which we don't know very well, because it's hard to know what the plasma content of any other galaxy is. But you can see the black line here in this relation is actually the Planck prediction. If you take omega baryon, assume it's fully ionized, as it should be, and the gray region is the cosmic variance you would expect, because the lines of sight to different FRBs will intersect with different galaxy halos in the full cosmic web. So even though there's just a few data points here, and this is the original Macquart plot, it clearly signaled the importance of fast radio bursts for understanding large-scale structure and cosmology, identifying in this case for the first time observationally the quote-unquote missing baryons. Now, I believe that this has a huge potential for studying large-scale structure. Different simulations of the cosmic web predict different statistics for fast radio burst dispersion measure distributions, for example, and different macquart plots. There's a very rich field here that I don't have time to go into, but I wanted to highlight the importance. And here is one of the latest, more recent macquart relation plots, where, sorry, redshift is on the x-axis again, and the dispersion measure in the intergalactic medium is on the y-axis. You see there's a lot of scatter. In this case, this is one of the furthest FRBs that has been detected, at least by the ASCAP team, out to redshift of 1. But wouldn't it be nice to fill this plot with thousands of fast radio bursts? That would be extremely informative about large-scale structure and circumgalactic media around galaxies, the nature of feedback within those galaxies that creates those circumgalactic media, galaxy halos, et cetera. Keep that in mind, because I will come back to that point. Now I want to switch to talk about the CHIME telescope in Canada. This is the Canadian Hydrogen Intensity Mapping Experiment, and you notice there's no fast radio burst in the name CHIME, and this is because the telescope was designed for a totally different purpose, to map neutral hydrogen gas in order to measure baryon acoustic oscillations and study the accelerating expansion of the universe, a project of which I am not involved. However, it turns out this wonderful revolutionary telescope is fantastic also for finding fast radio bursts. It's located at the Dominion Radio Astrophysical Observatory in Penticton, British Columbia, and it consists of 4 cylinders that are measure 100 meters by 20 meters. So in Canadian units, the total collecting area of CHIME in Canadian units is 5 hockey arenas. I'm a big hockey fan, you might not know that. It has no moving parts. This telescope is oriented exactly north-south and just looks at whatever is overhead and studies the sky as it rotates from east to west overhead. Along the axis of each cylinder are hanging, and you can't see it in this picture, but I promise you they're there, 256 dual polarization antennas that are fed with an elaborate cabling system, thousands of cables, into the world's largest correlator that reads in 13 terabits per second. That's comparable to the entire world cellular network, all being read in real time and analyzed on computers that are located in shipping containers that are adjacent to the telescope. We're sensitive in the band 400 to 800 megahertz. And what's spectacular about CHIME is that it has enormous field of view. So because the cylinder only focuses in the east-west direction, we have a beam that is 120 degrees in the north-south direction. So our total field of view is over 220 square degrees of the sky, orders of magnitude greater than any other radio telescope. And so we observe the entire northern sky, and by northern, I mean north of -11 declinations, so more than the northern sky, every single day. And our efficiency is about 96%, so we're almost always online. The signal path is quite complicated. Without getting into too many details, you see the cylinders go through this powerful FX-style correlator, and then is divided into 3 different back ends, currently 3, we can add others. One is for the cosmology that I described, one for fast radio bursts, and another for pulsars. And these all operate simultaneously. We do all this science 24/7 every day. Here is the CHIME fast radio burst team standing next to CHIME, so you can see for scale. And here is from our latest meeting. I want to emphasize this is a project that is run by brilliant and hardworking graduate students and postdocs. We have very few professional staff. This really, really wonderful team, and I'm accepting the award today on behalf of these people because they really are what make this project work. Now that full large 220 square degree field of view is divided by this correlator into 1,024 independent digital beams. So you see these beams now going from the lowest declination, that would be the furthest south, all the way to the north, and we have 4 in the east-west direction. And so having this telescope with these 1,024 digital beams is like having 1,000 green bank telescopes all operating simultaneously, look at different parts of the sky. And each of these beams, we search for fast radio bursts in real time. Our detection pipeline is, it's trigger based. We cannot save all of the data that we're analyzing. We must make quick real-time decisions about when we detect a fast radio burst. If we miss a fast radio burst because our pipeline, isn't optimal, it's gone. We lose it forever. So we have a trigger-based system, and we buffer data. And everything is sitting inside those shipping containers adjacent to the cylinders. And you see we have an intensity data buffer that we save. We're constantly buffering data. And if the real-time software detects something, it dumps that buffer, and then we save it. We also have a raw voltage, we call it a baseband buffer, that saves the data at a much higher time resolution and also maintains full polarization sensitivity, so that we're searching the intensity data buffer at a cadence of 1 millisecond. But if we detect something, we can also save the raw voltage data and have sensitivity at time resolution as high as 2.5 microseconds, as well as full polarization information. This is the cumulative number of detected FRB sources as a function of time. You can see the lower plot is represents the cumulative distribution of fast radio bursts that are localized on the sky with a wide field interferometer like the ASCAP telescope in Australia. And that's the one that currently can identify locations of fast radio bursts. Another such instrument is the DSA 110 that's run by Caltech. It also can localize immediately. CHIME does not localize very well. Our individual beams are about ½ a degree on the sky. So it's hard for us to localize with great precision, except for fast radio bursts that are very nearby, where the number of host galaxies that's plausibly connected is very small. So for the vast majority of fast radio bursts, CHIME cannot yet identify the host galaxy. But what we cannot do, we make up for in numbers. You can see the logarithmic scale here. We've now detected many thousands of fast radio burst sources on the sky. And there we see that was the when we first started publishing. So this is what it feels like sometimes to be on the CHIME fast radio burst team, but that little girl will be fine, don't worry, and we're okay too, but sometimes it feels that way as a team member. This is to whet your appetite for our second CHIME catalog, which we're busy preparing right now, over 4,000 sources. We haven't, it's still in preliminary work, lots of interesting things. We also have detected many, this is our first catalog that we published in 2021. You can see a sample postage stamps of some of the over 500 events that we published. With a large statistical sample on the sky, we can determine things like the log N, log S distribution, the cumulative fluence distribution with, there's the power law index is consistent with, the standard -1.5, which is as expected for a non-evolving population in Euclidean space. And this is because fast radio bursts detected with CHIME tend to be, the distribution in redshift space peaks around 0.5. So we do detect them out to redshift 1, 2, but the numbers are dropping. And we believe in the second catalog, we might start to detect cosmology with them. Here you can see the DM distribution from the first catalog. The above on the top, the line plot over there is showing you our selection function. So we're very careful when doing these large surveys to determine our instrument biases. That's very, very important in understanding the population. You see there's only a modest instrumental bias against detecting the high dispersion measure events, and you can see the distribution on the right that's now been corrected. Whereas in the bottom plot, you can see the selection function for highly scattered events. We are very insensitive to highly scattered fast radio bursts. We detect some, but we know we don't detect most of them. And we absolutely in population studies must correct for these biases. After doing so, we can determine the volumetric rate of these sources, something like 70,000 per cubic gigaparsec per year. And we can determine things like their energy cutoff, assuming a Schechter function, characteristic energy cutoff around 2 × 10⁻41 ergs. And if you would like to study chime fast radio bursts, you can go to this website and sign up for our VO event service, and you can receive an email every single time we detect a fast radio burst. I'm sure you all want that on your cell phone. Now, because chime studies the entire northern sky every day, we are very efficient at finding repeating fast radio bursts. So from the one that existed before, that was known before chime turned on, we now have 50. Many, you could see examples of them. They're color-coded by source. So the green ones are all the same source on the sky. You see very interesting morphologies, multiple peaks in many cases. And you'll also notice here the dispersion effect has been removed. You're seeing now each fast radio burst de-disperse from 400 to 800 megahertz. You see many of them are band limited. That is, they're not broadband. They don't cover all the radio frequencies like most fast radio bursts do. This is very interesting. We don't know why it is, but it's true. And they tend to drift downward in a sad trombone effect to mimic. Why do we call it sad trombone? Because, you know, the trombone goes wah, wah, wah. And that's what fast radio bursts do also. The frequencies descends with time. We don't know why. We are actively preparing another fast radio, repeating fast radio burst catalog. Postdoc Amanda Cook is working on that. Here you can see the clear difference. Once you have enough statistics like we have, you can compare repeater and non-repeater morphologies and spectra. So on the x-axis is the pulse width, and on the y-axis is a measure of narrow bandedness. So 0 corresponds to something that's very broadband. And you see the green points are the non-repeaters, which tend to be very broadband, whereas the orange points, the repeaters, tend to be very narrow band. And similarly, you could see that the one-offs, the ones that don't yet repeat, tend to be much narrower than the repeaters, which tend to be broader and have very complex morphologies. And the reasons for this does this mean they're different populations? Does it mean there's different emission mechanisms? We don't really know. I can say very quickly that in the latest repeater catalog, we've discovered that the dispersion measure distributions of repeaters and non-repeaters are different. At over the 3 sigma level, repeaters tend to have lower dispersion measures. And we believe this is true and must be true for any population that has a luminosity function where there's more faint sources than bright sources. And it's because to call it a repeater, you need 2 events. The second one has to be dim. So typically we'll be closer. At least qualitatively, that's true. We've discovered periodic sources. So, you know, there's the survey kind of science that you can do by having hundreds of them. But if you have hundreds, you can also identify unique, remarkable individual sources like the first periodic repeater. Here you can see this is now data from 2018 through 2019. The exposure in the top plot is the horizontal black line. That is, we can always see the source, or almost always see the source on the sky, but the red triangles are where we detect bursts, and those only happen in 4-day windows every 16 days. And this pattern has been repeating now continuously since 2019. Very, very predictable. It's a clear periodic source. What kind of source is it? It smells 16 days, sounds like a binary system. We don't have any other evidence for the binary. You can look with Hubble Space Telescope at the position of the periodic repeater, which is in a spiral galaxy and sitting just outside a star formation region. So we know it's young, but it's not extremely young. And we put that in contrast to other fast radio burst sources that have been found inside star formation regions. So they're young, but are they, very massive stars? We don't know. Now, we also detected luminous fast radio bursts from a magnetar inside our galaxy, SGR 1935 plus 2154. Here you can see it actually had two different bursts, just a few milliseconds apart. And this occurred simultaneously with an X-ray burst that was just a few milliseconds off from the radio burst. So this is a magnetar, and it tends to support the idea that fast radio burst sources could be magnetars. This is now an important plot that shows distance on the x-axis and fluence, that is, a measure of flux on the y-axis. The galactic radio pulsars are the blue points in the bottom left corner. And the fast radio bursts at much greater distances, but comparable fluences, are shown on the bottom right corner. And you see, we don't really, in cases where we haven't clearly identified the host galaxy, we don't exactly know their distance because we don't have a redshift for those sources, only for the ones that are localized. And the diagonal lines are lines of constant energy. So you can see that the galactic radio pulsars, including the crab that has giant pulses, tend to have much, much smaller energies than the fast radio burst by many orders of magnitude. This isn't subtle. By factors of millions to billions, up to factor of 10 to the 12 times less energy than the fast radio burst sources. The galactic magnetar that we detected is up there at the top of the plot. And so it's at low distance, it's in our galaxy. But you can see that its energy, if you follow the line, it nicks the bottom of the least energetic fast radio burst sources that we know. So if you took this galactic magnetar and you put it in nearby galaxies, you would detect it as a fast radio burst. But there's many orders of magnitude luminosity left to cover. We don't know if magnetars can produce those sorts of luminosities. We've also found a very nearby fast radio burst. This is in the Grand Design Spiral Galaxy M81, which is only 3.6 megaparsecs away. It's sitting outside the optical disk in the H1 disk. And curiously, this one happens to coincide with a globular cluster. So this was a great shock because globular clusters are made of old stars. You do not expect to find a magnetar, at least the magnetars that we know and love in our own galaxy. You do not expect to find such a source in a globular cluster. Now, we said it seems like, they're in star formation regions, magnetars. You think FRBs should be young objects. Why do we find one in a globular cluster? We don't know the answer to that. And new deep X-ray observations at the times of radio bursts show no X-rays, and we can rule out magnetar giant flares for this particular source, at least, modulo beaming. Now, we do have one fast radio burst source that has a sub-second periodicity. This is a single burst, has never been seen again, that consists of 9 components that are separated very precisely by a constant time interval of about 200 milliseconds. This is the significance of the periodicity in this one burst is about 7 sigma, so it's very, very significant. We have not yet detected any other fast radio burst with a signature. We have some that visually look periodic, but when it's only 5 or 6 individual components, it's not statistically significant. So, you know, this smells, this is consistent with being periodic with a period of 200 milliseconds, which would be like a radio pulsar. We have a new source. Very quickly, I'll say, I've run out of time, so I'll have to do it very quickly, but a very remarkable source where highly linearly polarized, so you can see the burst there. The red is the linear polarization, and the black curve at the top is the position angle of the linear polarization as a function of pulse phase. And for those of you who know about radio pulsars, you will remember that when you look down the barrel of the beam of a radio pulsar, you see magnetic field structure that as it traverses the line of sight, the position angle swing of the radio pulsar traverses this S wave, this famous position angle versus phase plot, that S curve. This is something seen ubiquitously in radio pulsars. And here now, and it is explained very well by the rotating vector model, a simple geometric model of a rotating beam with a fixed magnetic field. And if you fit this to the position angle swing of this CHIME FRB discovery, it fits beautifully. So we think this is another interesting signal that this could be coming from a neutron star. And in the last minute, which I hope the chair will give me, I will just say that we're now planning outrigger telescopes for CHIME fast radio bursts to do synoptic VLBI, very long baseline interferometry, across the North American continent using CHIME as a signal, as a trigger. We have 3 outrigger stations being built at different locations, and the goal is to sky localize 1,000 fast radio bursts to 50 milliarc seconds and determine unambiguously redshifts and even for close sources, locations within those host galaxies. And this is a technique. Synoptic VLBI is non-trivial. It is not easy to do VLBI on an object that occurs where you can't predict and lasts only for a millisecond. If those of you do VLBI know it's not easy, but we've already shown that it is possible using a temporary interferometer. These are the 3 CHIME outriggers, one near Allenby, British Columbia. It's already built, it's in full science mode, and we've just done our first science with it, localizing a very active new repeater. And if you watch ATELs, you saw these last week, 3 ATELs announcing the first VLBI localization of fast radio bursts. The second outrigger is in Green Bank, West Virginia. You can see here some of the students who helped to set this thing up. And it's very close to science operation mode. And the third outrigger is coming soon, Hat Creek, California, at the site of the SETI Institute in the Allen Array. We hope to have this commissioned by the end of the calendar year. And in summary, fast radio bursts, we still don't know what they are. Could there be multiple classes? Perhaps some are magnetars, perhaps some are older objects, we don't know. There's a variety of phenomenology, host environments, and they have great potential as novel probes of large-scale structure, of the missing baryons in the intergalactic medium, and of circumgalactic media. And there's new exciting instruments coming online, and thank you very much for your attention.
Thank you very much. And time is running down, so maybe one short question. There is one in the background.
Can you estimate the upper limit of the non-repeating fast radio burst at this time? Limit frequency of the
Do you mean the rate? The number of non-repeating or the repeating rate of non-repeaters? So if you mean the rate, the repetition rate, non-repeating bursts, we have some where the rate is much lower than that of repeating ones. But if you mean the volume density of them, it's,
no, I mean the predicted 10 years before discovery of fast radio bursts, we with my postgraduate student predicted fast radio bursts as a precursor or merging 2 neutron stars. That is a revived radio pulsar revive it by orbiting millisecond as a, you understand?
Yeah, I'm not 100% sure what you're asking, but
Can you close the non-repeating radio bars?
can we close non-repeating?
Yeah.
Can we say they will they won't repeat?
What is enough? Yes.
I wish I knew what you were asking. Let's talk in the coffee break. I promise you,
maybe-
I'll answer your question there.
Maybe, but thank you again. Thank you very much again, and really. Next talk is remote, and we need a connection to Michael Gramme. Is that possible? I asked. Oh, here is. Michael, can you hear us?
Yeah, Hans-Jörg, thank you very much. I can hear you. Can you hear me too?
Yes, well, very well. Here sitting roughly 200 people waiting for your contribution. And we don't have any information about the title, but you will tell us. Please, it's on you.
Yes, thank you. I was asked actually to look back in history and review some of the anniversary celebration that we have this year for the 50-year anniversary of discovering the Howard-Taylor pulsar. But before I do that, let me congratulate Dee and Vicky and the teams for their achievement, and congratulations to receive the award. And Vicky gave a nice introduction about a few things that I will also mention in my talk. So it's very fun. I tried to share my slide. Let me try to see if you can see this in a second. Wait. I can see that. Okay, I can actually see my own slide on the screen. Excellent. Thank you. So yes, so 1974 marked the year when Russell House and Joe Taylor discovered the first binary pulsar, and kind of started a new era of testing relativistic gravity, in particular a very precise way, as I'll try to demonstrate to you in the following, and I'll show you some updates of what's going on at the moment. But of course, there's so much more that needs to be reported on, so I'll just focus on a few items here. Let me go back to 1967, which is when the research field of pulsars was founded by the discovery of Jocelyn Bell, doing a PhD with Anthony Hewitt in Cambridge. And of course, you all know the story, so I won't bore you with the details. But of course, in the amazing discovery paper, they were discussing all the models already, including vibrating white dwarfs, but also rotating neutron stars. And it was then the discovery of the Crab pulsar and the Crab nebula with a period of 33 milliseconds, which nailed the model of a rotating neutron star, and therefore a lighthouse in space where the pulse is attached to the rotation of the neutron star. And the potential of pulsars for testing fundamental physics, in particular gravity, I think was soon realized. And if you do some literature research, one of the first papers that I come across, but maybe this is not the first, but so apologize if I just talk about this one here. This is a paper by Kip Thorne written in January 1969, where he already points out that if pulsars are in a binary orbit, the orbit should shrink and the period should decrease, the orbital period, due to the emission of gravitational waves. And he already has the correct formula in this paper. And it was January 1969. But we had to wait a few more years until the first binaries were discovered. And I was just entering primary school when Joe Taylor and Russell House used the Arecibo telescope, which unfortunately, of course, collapsed not that long ago. There's a small picture here where you can see actually how the telescope looked like when they used it. They found the first binary pulsar, the first pulsar with a companion, and it was a stroke of luck because now we know that finding a pulsar that is orbiting by a second neutron star, as they did, is actually rather rare. From the many few hundred binary pulsars that we have discovered by now, only 20 or so have actually a neutron star companion. Most of the others have white dwarf companions. But they discovered it. The first one to be seen was a pulsar with an unseen second neutron star in an almost 8-hour orbit. And you can see from the radial velocity curve inferred from the Doppler shift in the observed spin period that it is a nice eccentric orbit. So that was in discovery was made in 1974. The paper just appeared in January 15. I come back to that later on. It took only 4 years until the Texas Symposium and then until this paper came out, where Joe Taylor and colleagues could indeed present the first evidence for the shrinkage of the orbit and hence the emission of gravitational waves. So that was the first evidence that gravitational waves indeed existed. And I should also point out, of course, one of the persons who's sometimes not mentioned, but did an amazing part of the work was Joel Weisberg. And here's the plot of the latest update on the timing of the Hals-Taylor pulsar that he published with his students in 2016. And the importance of that system cannot be overstated because apart from the shrinkage of the orbit of about 1 centimeter a day and the proof that gravitational waves exist, the energy, as you can see, the red line's prediction of particle emission by GR fits exactly as predicted by GR. You can argue that this also shows the gravity propagates at the speed of light. And what was also not clear at the time is that GR also applies to strongly self-gravitating bodies. And of course, the fact that that system collapses at some point and merges into neutron stars was good motivation to build the ground-based detectors like LIGO to search for these events of gravitational wave bursts once they collapse and merge in the merger. I just want to point out this paper. This is the original Scientific American paper from 1981, first authors by Joel together with Joe Taylor and Lee Fowler. I read this when I was at high school, and maybe I didn't know it at the time, but it fascinated me. And somehow I'm quite lucky that I was able to sort of work on this field later on. Maybe unconsciously, this paper guided my career. I have no idea, but it's very nice memory for myself. The other paper that I cherish, I have to say, is this paper by Thibault Damour and Joe Taylor. It came out in '92, which is sort of the go-to Bible of what you would do with binary pulsars. And it's based to some extent on the wonderful work that Thibault did with Nathalie Durrell. And these are two papers which are difficult to find in the library, but I should recommend it for everyone to read it. And of course, there's also the paper which appeared actually earlier than the discovery paper in January 1975. This is the paper that Thibault and Bremo published in December 1974, 23rd of December, that's a Christmas present, where they proposed that one should look at the effects of the geodetic precession or relativistic spin precession in general, in particular in the pulse profile that we would observe. And so this paper indeed points out that we can learn more about from the pulse structure, whereas this is also included in the 92 paper by Thibault and Joe, but also, of course, the timing information. So I'll talk about the timing information first. There's some ambulance out there. I'll talk about the timing information first, and then talk a little bit about pulse structure information. So pulsar timing is in principle very easy. You just take some sensitive telescopes, you observe the pulses as they are emitted from your source, propagating through the interstellar medium, and you do some data analysis after time tagging the arrival of the pulses, and you apply a timing model, and all outcomes out at some gravity test or maybe equation of state constraints or whatever your favorite fundamental physics is. That is easy if pulsar is orbiting in the Keplerian orbit, but if it's not, if you have relativistic effects, you should take these effects into account in a way that is theory independent. And so I'll briefly summarize, you all know that, but let me just do it in anyway. The post-Keplerian theme that we use to test our theories in a theory independent way. And it's quite easy for any reasonable theory of gravity. Your measured deviation from the Keplerian orbit can be parameterized by the post-Keplerian parameter, which itself is just a function of the two masses of the system, the pulsar mass and the companion mass. And so you can rewrite those relationships to draw a line in a mass-mass diagram, as we call it. And the shape and the functional dependency on the masses is given by the theory of gravity. And the location, the scale of the curve is given by the measured Keplerian parameters. For instance, I showed you this formula already for the decay of the orbit due to gravitational wave emission. You can see it's a function of the Keplerian parameters here, eccentricity and orbital period, and the two unknown masses of the pulsar and its companion that describes this curve in this diagram. If you measure a second post-Keplerian parameter, for instance, the orbital precession or Shapiro delay, come back to it in a second, you get an intersection point in your mass-mass diagram, and if you believe your theory of gravity, then this gives you the two masses of the system. And that's how we measure this amazing range of masses that you can see here on the lower left. That's an up-to-date representation of the masses that we have obtained using this technique. And you can see that for many of these masses, the error bars are much too small to be shown on the scale. If you measure at least 3 post-Keplerian parameters, then the theory can be tested, because in that case, the third line should intersect in the same intersection point of the first 2 lines. If that isn't the case, the theory needs to be rejected because it doesn't describe the data consistently. But if it does, like here for the Hauss-Taylor pulsar, you have a test of GR. For n independent measurements of post-Keplerian parameters, you get n-2 independent tests. And this, by the way, is the update that Joel Weisberg and his student published in 2016. There is now also a hint of Shapiro delay, as you can see here with this back fat line. The line thickness is indicating the precision of the measurement, the uncertainty is ±1 sigma. And you can see that for the orbital precession, omega dot, the PV dot, decay of the orbit, and the gravitational redshift gamma, the precision is extremely high. But for the Shapiro delay, it is not quite comparable what we do with other pulsars. And the other pulsar, of course, that the crown jewel still is the so-called double pulsar, because here we have actually 2 active radio pulsars orbiting each other. The orbit is inclined, very fortunately, to almost 90 degrees, a deviation of only 0.65 degrees from perfect alignment with the orbit. And that allows us to measure a wonderful range of different relativistic effects, which are listed here on the right. I will not go through them, I'll just highlight a few of them. We have, for instance, also a precise VLBI distance to this pulsar. And indeed, it's much closer than the Hauss-Taylor pulsar, which also makes it very good for testing gravitational wave emission, because some external contributions to the observed period decay are negligible to some extent, at least in this, at the current precision for the double pulsar. We have about 1 million times of arrival measurements that corresponds to an average cadence of a measurement of less than 10 minutes. And we have covered 300 degrees of precession of the orbit and more, so we can measure the periasteral advance to ridiculous high precision already at the 35 sigma level at the contribution of the second post-Newtonian effect. This is important if you want to measure length steering and the moment of inertia. I'll come back to that in a second. The gravitational wave emission for the double pulsar looks like this, the same parabola plot as shown for the Hauss-Taylor pulsar, here shown on the right. The precision is so good that we have to take into account that the system is actually losing mass by emitting electromagnetic radiation. The pulsar emits and loses 8.4 million tons per second, at 3.2 times 10⁻21 masses of the Newton star A. but because the energy is equal to a mass, we have to take this into account. It's a sort of our error budget. The precision at the lowest post-Newtonian level is 3 orders of magnitude better than what LIGO can do, and the precision of the test is actually quite well. And this is the best, most precise test of the gravitational wave quadrupolar formula that is existing at the moment. I mentioned the Shapiro delay for the Hals-Taylor pulsar. If you do this for the double pulsar, it looks like this because the orbit is almost inclined. The pulsars have to pass the second pulsar on the way to Earth in just 10,600 kilometer distance. That leads to this beautiful Shapiro delay curve with a maximum delay of about 100 microseconds. And that allows us to measure both the masses as well as the inclination angle of the orbit very precisely. And again, the agreement with GR is amazing. We can use this actually to look for small deviations of the standard Shapiro delay curve. If you go to a higher order, you have to take into account that the masses are actually moving while the light is propagating through the orbit. That is the 1.5 pn Shapiro delay, but also at the same time, so this leads to a small shift in the curve, but also at the same time, we have to take light bending into account that the light is deflected in a gravitational field of pulsar B, so the pulsar A has to shoot its photon at a slightly later phase to be compensating the bending, and after Fourier conjunction, you have to shoot the photons of pulsar A slightly earlier, and that leads to this characteristic curve here shown on the left, which also tells the direction of the spin that the pulsar A is orbiting prograde to the orbital angular momentum vector. And again, it allows to do some tests of GR. What is amazing, if you do the same experiment with MeerKAT, which is this new wonderful telescope in the southern hemisphere, you can do the same experiment rather on a time scale of 16 years. We published a couple of years ago. You can do this within 3 years with a completely independent data set, and you can see the same effect. This is here work by our PhD student postdoc Huan Chen Hu, where she discovered the same signature independently in the MeerKAT data with just 3 years of data, and that just shows you the amazing power that the MeerKAT telescope has over the northern hemisphere telescopes that exist apart from FAST, and I'll come back to FAST in a second. Putting it all together, this is the mass diagram for the double pulsar. We have 7 post-Keplerian parameters plus the theory independent mass ratio, which is here, all intersect in a beautiful line. Let me zoom in. Here, by the way, on the right, you can see the GR test. GR all passing flying colors. Zooming into the mass diagram, just to the intersection point, this is here you can see the uncertainty of our measurements. And this line here, there's from top left to bottom right is the K of the orbit. The uncertainty, unfortunately, is still large in the sense that if you want to compare it to the lines of the Periastian advanced omega dot, you still have some freedom where to place the intersection point. And in fact, the intersection point moves if you take frame dragging into account or not. Without frame dragging, the intersection point would lie here. With frame dragging, and take into account the intersection point lies there. And if we were to, and that's the goal for the next years, if we shrink the uncertainty of the orbital period decay line such that the intersection point is well determined, then we can use the lens steering effect to actually measure the moment of inertia of the Newton star, because it contributes at the second post-Newtonian level to the observed Periastian advance. That's the shift that you have just seen. And in fact, that shift depends directly on the moment of inertia of pulsar A. And we have done this experiment now for a few years. We are only able to get upper limits so far, but we can already use this pulsar timing, nothing else, to constrain the radius of the Newton star to 22 kilometers at 90% confidence. That's, of course, much worse than what experiments like NICER and then also LIGO and others can do. But we can predict in this work by Huan Chen that we can get a 10% measurement in a few years' time if we continue our observations with MeerKAT. and later the SKA. That brings me to relativistic spin precession in general. There is the effect that Remo and Thibault had predicted in 1974. Similar experiments, of course, have been done with gravity probe B in the weak field of the Earth. But going back to that paper, if you have a misalignment of the pulsar spin with the orbital angular momentum vector, which is naturally occurring if the supernova that gives birth to the second neutron star has a kick, and that kick makes the newborn orbit slightly misaligned with the previous orbit, then you get this misalignment between the pulsar spin and the orbital angular momentum vector, and in that case, you should see geodesic precession where the pulsar spin precesses around the orbital angular momentum vector. As a result, the line of sight, how we cut our emission cone, will change the function of time. This is demonstrated here in two still images taken from an animation that I won't show, because I showed this at this venue before. Oops. But that leads to this variation in pulse profile. There was some earlier work by Roger Romani and George Taylor trying to detect this effect. What they did find is that the amplitude ratio, these two peaks in the pulse profile, changes the function of time, whereas the width was constant. The width should not be constant. We would expect the width to be going down with time or increasing depending on which phase of the precession we are. And indeed, that was the evidence that we presented at the end of the 90s based on Ethelsberg data, where we could see for the first time that the profile is indeed becoming narrower with time. At the time, I predicted that the pulsar will disappear in 2025. It's still visible. The other prediction that I made, this is from an animation I showed in the Master Grossman meeting in 2000. This is, I predicted that if the beam shape looks a bit like this, then the amplitude ratio should start to go up again once we are coming to the edge of the cone. Now we have observed this pulsar with Ethelsberg ever since. This is the result of a PhD thesis, the paper that's being written up. And you can see that this is how the profile looks like as a function of MJD. And indeed, the profile does become slightly, the amplitude ratio becomes slightly equal. Again, this is polarization data that we have taken also. Vicky already pointed out the rotating vector model in the S-like swing. The data may be difficult to see here, but what the home take message is that the position angle becomes flatter with time, which in the speak of the rotating vector model means we're moving further away from the magnetic axis. If you do the polarization and the total power modeling, the spin axis is misaligned with the orbit by about 20 degrees, which is consistent with the earlier modeling that I did at the end of the 90s. So that is consistent, and we're trying to, but we can say it's probably not a nice hollow cone-like shape, but we do see the change in the amplitude ratio. These are some measurements and some very temporary preliminary fits, but you can see that it's actually the amplitude ratio is flattening out. And in fact, there is some hint that it's actually increasing in the latest measurements. So this is actually as predicted almost 20 years ago, or more than 20 years ago, but wait for detailed modeling of the beam shape later this year when we publish the paper, hopefully together with the anniversary of the House-Taylor pulsar. This is the pulsar becomes a bit weaker, as you would expect if you're moving out of the beam. This is some meerkat measurements, beautiful S-like swing as the rotating vector model suggests. So this is fully consistent, also seen with other telescopes. Coming back to the other pulsar, where we see geodesic precession as well. Here, the precession of pulsar B has caused pulsar B to disappear temporarily. It may be back in time, depending on your beam modeling. We had predicted it being back by now. It's not, so we have to adjust our beam modeling. There's a paper by Marcus Lower using meerkat data where this is updated. And then this is the work that, of course, Vicky knows very well because it was done by René Breton when he was a PhD student, where we use the eclipse that is caused by the torus of the magnetosphere of pulsar B eclipsing the background pulsar A during half the period, and then eventually it changes the separation of the visible light in the bottom from half a period of B to the full period of B, which depends sensitively on the spin axis. And if you let the other animation run, you can see that this is a function of time. So this allowed René to do a test at a 13% level of the precession rate that was predicted. We have updated, apologies that the left diagram is a bit blurry. This is the updated experiment with Meerkat. This is just the first step of an analysis, but even in this first step, you can see the beautiful data from Meerkat showing the eclipse. We already improved the test by a factor of 2, so we are now at the 6.5% level. That's the mathematics diagram that Marcus has derived. This is just based on Meerkat data alone. The next step, we're trying to do joint analysis with the old GBT data, which gives a higher leverage arm, and then we will expect that this will possibly become the best test for geodetic precession that we have by then. Until then, the best test, and maybe still the most beautiful test in a way, is given by this double Newton star system, 1906-0746. This is the young, second-born Newton star that we see. But the nice thing about this one here, with the spin axis is more or less orthogonal to the spin axis, we can see the North Pole and the South Pole of this pulsar. And again, you see this beautiful S-like swing where we pass the cone for the North Pole and the cone for the South Pole. And the sign of the slope tells you on which side of the magnetic axis you are. So for the North Pole, the slope goes upwards, so we are at the bottom below the magnetic axis, and the opposite for the South Pole. But the beauty about this is we have monitored this pulsar also for 15 years or so, and during that time, our line of sight for the South Pole crossed the pole from the north to the from the top to the south, and that means that the rotating vector model swapped, and in the slope, so we had from a negative slope above the magnetic pole, we now have a positive slope below the slope, and the pulsar is actually moving out of the line of sight, and needs telescopes like FAST and Meerkat to actually still be able to detect it with some reasonable sensitivity. And we have compared this to the prediction rate of the R, and it fits beautifully. Coming to the end of my talk, this is the list of double Newton stars and also pulsar 1 pulsar white dwarf system that we also know very well, where we have detected geodetic precession as predicted by Thibault and Remo a long time ago. Wherever the precession rate is high enough as predicted from the orbital parameters, we see it. And this is even true for very difficult cases where the effect is subtle because the geometry is unfortunate. But I just want to point out this paper by Lingji Meng using FAST data, where we have looked at this new double Newton star system 946 plus 2052, where you see on the left-hand side a number of pulse profiles that show subtle differences as we observe the time, particularly in this first component, and it really needed the sensitivity of FAST to unravel that effect, and but even there we can see this. So it's an effect that we can now routinely observe in relativistic binaries, and we make huge use of it because it tells you something about the beam structure of the pulsar. And that brings me to my end. I think the journey that started with Jocelyn in 1967 and then ushered into this new era with the discovery of binary pulses by George Taylor and Russell Hulse, that was awarded with a Nobel Prize, of course, has given us some beautiful results and beautiful laboratories to play with. They're providing often unique, but certainly very precise strong field tests of gravity. I haven't talked about how we use this to constrain alternative theories of gravity. That's a completely different talk. But look at the double pulsar paper from 21, where we gave some introduction how we do this. The measurements that we have are usually clean and precise. The confirming GR at the highest, most precise level in strong field conditions so far. We have shown that geodesic precession opened a completely new source of information for gravitational physics as well as for astrophysics, because we can study the pulsar beams. And geodesic precession is sometimes observed in some surprising ways, like in the eclipses of the double pulsar. And I still think it's unfortunate that Einstein didn't live to see the discovery of pulsars, and in fact, most of what radio astronomers can do. And I'm sure you would also be excited of FRBs. And this is I'm sure you actually seen this before, but this is my favorite quote of Albert Einstein. He wrote that in a letter to Arnold Sommerfeld when he was first discussing that his field equations were able to explain the perihelion advance of Mercury, which of course was measured by precise astrometry from optical astronomers. And he says there comes the pedantic precision of astronomy to the rescue, which I have ridiculed scientists so often in the past. So I hope I could give you a little bit of what the exciting things that pulsars have done, with the current update on some specific pulsars. There's much more to be seen, but there's also much more to come. And I think I'll stop here. Thank you very much.
Michael, thank you for this presentation, precise in numbers and precise in time. Thank you very much. And maybe there is a question now here from the auditorium. Is there one? I can ask you. Remo.
As usual, I congratulate Michael for this beautiful presentation, which comes at a very special moment. Michael got the Marcel Grossman Award years ago, but it is very beautiful to see the development that you trace back to the recent days. But what I think is very exciting is that you have shown how fast can contribute to the last bit of looking at this old work that we did with Thibault. And I sincerely hope that Dilly and the fast people will continue improving this data. It's marvelous talk, marvelous, and thank you very much. And next time you have to come in person, but the quality of the projection, which we have in Pescara, is so high that we did not miss your presence, because the quality of the images is just superb. Thank you again, and thank you to everyone.
Thank you, Remo. I have to apologize not being there because we have the SKA council meeting in parallel. So I need to dash back to that council meeting in a second. And then, of course, the SKA in the Southern Hemisphere will produce other beautiful results this far together in the North. Thank you very much. Thanks for your attention.
Thank you again, and see you next. Okay, bye-bye.
Bye.
Before we come to the next presenter, there's a break. Organizers asked me to make the break now, go out for the photograph, taking the photograph, and then having a coffee break and come back here at 11:30 for the remaining 5 contributions. We go on, and the next speaker is Xiongnan Sang. He will talk about HXMT. That's not him, yeah, but can we have his presentation, please? Please. We need a presentation of Professor Sang. No, we need a presentation. 2 minutes. So we have to wait a little bit.
So they prepare for the call after me, that job, the session, basically.
That's why we have a break.
Yeah, that's why I'm afraid.
But they are there. Ah, okay, now we have it. Now we can, again, Professor Tang, take over and please.
Okay, good morning. I'm so pleased to be here today. And I'm going to present the highlight of the InSight HXT mission and also a future project related to this mission. And I want to, if this works, it doesn't work. So how to make this work? Oh, okay, that's a switch, okay, the modern technology. Okay, I just start with congratulations to the prize, the award winners, in particular to my colleague, Professor Li, and he's related somewhat to my talk, as I will show you. And InSight HXT is China's first actually satellite. It has a very long history. It was proposed in 1993 by my advisor, Professor T.P. Li. You recognize the last name is the same as Li. It's not a coincidence. He is the father of Professor Li, who won the award today. And but at the time, of course, Tilly was only 20 years old, so he didn't know very much about this. But nevertheless, since then, the team has developed this mission. Eventually, it was launched in 2017. The feature of this mission is that it has a large collective area, higher than 30 kV, with good timing and wide energy band. And since the launch, it has been more than 7 years, and the mission is still operating smoothly in orbit. And we focus, since it doesn't have a mirror, so we focus on bright sources, neutron star, black hole equation system, and gamma bursts, and fast radio burst is actually emission, and so on. And finally, I should say that it's in AO6, and this mission has a chunk of gas observation time is open to the world. And according to the status of the satellite, it will be in orbit for a few more years. We hope we will still deliver interesting science to us. As you can see on the top of the satellite, we have the group of instruments. As I show on the right, the effective area from X-ray to higher energies and gradually to the very high energy, will have a very large effective area. It in fact is also a gamma burst also can monitor in high energy band all the way to about MeV energy range. And first, I want to talk a few cases of the neutron stars that we have done with this mission. And we know that it's a very complex interaction between neutron star and the accretion disk. And the one of the very first sources we have observed extensively is this galactic ultraluminous X-ray sources, SWIFT 0243. As you can see, since the outburst, we almost continuously observe the bright part of the outburst. In total, we have more than 100 pointings with a lot of, as you can see, more than nearly 2 million seconds of exposure time. So therefore, a lot of papers have been produced from here. And one of the results is that during the evolution of the outburst, we have seen evidence of the gas pressure dominated disk to radiation pressure dominated case. As we can see, the profile the changes at the supercritical luminosity, and we sort of have a picture that how it evolved from a low luminosity all the way to the high luminosity. Eventually, the disk becomes very thick. And at the low luminosity and from the spin down or spin up situation, we determined that this system has a low dipole magnetic field. Low means 10 to the 12 Gauss, basically, from this data. And then we have extensive spectral analysis of the system. We have seen spectral transitions, for example, at the different luminosities, and the typical spectral parameters have changes from this result, and seems because this spectral information comes from the accretion column, and we determined that we need a high magnetic field in the accretion column. So it seems we have a contradiction from the spin up, spin down history has a low magnetic field, then from the accretion column properties has a high magnetic field. Okay, then we detected a very high energy cyclotron absorption line, nearly up to 150 keV. Now from here, we can determine its surface magnetic field in the accretion column. And this is more than 10 to the 13 Gauss. Then compare with the 10 to the 12 Gauss dipole field, and we propose that in this neutron star system, we have evidence for multiple pole magnetic field. We have a dipole field, it's 10 to the 12 Gauss, then the multiple field 10 to the 13 Gauss from this result. As you can see, since the significance is so high with the detection, we can see the spin phase modulations of the cyclotron features through the spinning phase, and this can allow us to determine the accretion column properties very nicely. Another pulsars we also have observed extensively is 0535 in 2021 that we detect the cyclotron energy. Also, we can see a transition of the trend of the energy as a function of luminosity in the middle panel. And more recently, we use the pulse-to-pulse properties of this pulsar. We see a more complex evolution of the cyclotron energy as a function of the luminosity. And this is quite hard to explain, actually. On fast radio bursts, we didn't detect the radio signal, of course, but however, we managed to detect an X-ray burst related to this fast radio burst. It was a coincidence because before this fast radio burst happened, 10 hours before that, I decided to point the telescope to this magnetar for other purposes. And coincidentally, at the time of this fast radio burst, we detected a very bright X-ray burst in all energy band, from all the way from 1 keV to above 200 keV. And in particular, at the peak of the actual outburst, we see two sharp features, very similar to the integral detection of these sharp features. And in time, it's precisely coincidental to the two pulses of the fast radio burst. So therefore, we decided that it must be the same event. And then we can localize this event within our field of view to see if this event exactly comes from this neutron star. And you can see in the image in the middle is the HXMT image of that. We don't have a telescope, but we have collimators. With the different orientations of the collimators, we can still decide where the burst happened. It's exactly on the location of this magnetar. So it indeed comes from this magnetar and within an accuracy of a few arcs minute. So within the field, there's no other bright object there. So we decided that this must be the event coming from this magnetar. So therefore, we identified this actual burst is the same event that has this fast radio burst. Gamma burst, you all know this bold gamma burst, the brightest of all gamma bursts. It turns out another coincidence that at the time of this gamma burst, HXMT was scanning the galactic plane in the same region, coincidentally. So therefore, not only we detected the precursor, the main burst, and also the afterglow of this gamma burst with the scanning technique of this satellite. And from the afterglow, as you can see there, we can determine there is a break in afterglow. From the break time is very early, about 900 seconds after the burst. Then from the break, we can determine the jet angle, which is very narrow. It's less than 1 degree. So, and also with the precise observation of the main burst, that we also determine the fluence of this gamma burst. So it is indeed the brightest one, more than 50 times brighter than the previous brightest gamma burst. So the other people studied this, that decided it must be several thousand years, only one of such bursts can happen. And this shows you how we decided this early jet break in our data from the afterglow measurement with our instrument alone. And with this break, now we can correct its energy and measure the E peak and so on to understand further what happened to this particular gamma burst. Then I move on quickly on black hole active binaries. That's our main observational target. And I will show you in this 1820, it was one of the brightest black hole outbursts since the launch of this satellite. And again, we observe this burst almost completely. You can see this from the beginning of the outburst until the first rebirth, then the last episode of the outburst, almost a complete history of that. Then from here, we detected also the quasi-periodic oscillations, and you can see that the QPO as a function of time, it evolves, increases and decreases and increases again, and things like that, okay? One of the result we reported is that the QPO from 1 keV all the way above 200 keV, the very high energy quasi-periodic oscillation. Previously, such kind of QPO, called low frequency QPO, was mostly detected below 30 keV. Now we put the energy up 200 keV. And more recently, with the new technique we developed, we can go to even higher energy, more than 300 keV. And with this high energy QPOs, we also see the lack of the QPO between different energy bands with respect to a certain reference energy band. And if we put all this together, we find out that the high energy photon comes before low energy photon. So previously, we have used inverse Compton scattering to explain this lag, but clearly this is not the case. And first, of course, the high energy photon comes earlier than low energy photon. Second, the lag time, you can see, is as long as 1 second. So therefore, it's very hard to explain such a result. And we propose a model that such QPO comes from a compact jet, accurate jet, very close to the event horizon of the black hole. And in this model, the high energy photon come closer to the black hole, and the low energy photon comes away from the black hole. So therefore, as been shown in this simulation, in this cartoon pictures, that when this jet precedes with the frame dragging effect of the black hole, and eventually the higher energy photon comes first from the jet base, and then medium energy, then lower energy photon. So therefore, we can see the lag between different energy bands. And the time difference simply reflects how the jet is twisted. Okay. And in our data, we also see a very strong reflection component. You can see the ratio between the continuous spectral model and the data, and you can see we see the strong iron line and also reflection bump in the data. And it was found, as you can see in the red picture, right now, found that the corona evolved with the time, that is, its size as it shrinks with the time. If that's indeed the case, when the corona shrinks, the reflection from the disk, getting closer to the disk, should be stronger. But however, we see the reflection component, reflection fraction, as you can see on top panel on the right, it actually decreases. So therefore, a simple model of the geometry size change doesn't explain the data. In order to explain the data, we propose that while the corona, its size getting smaller, and the material moving in the corona, in the jet, actually get faster and faster. So it's getting smaller, but the velocity is higher. And because the Doppler effect, we see a smaller reflection fraction. Okay, so that's our interpretation of the data. And we have also combined our data with a nicer observation, because nicer can cover low energy band with good statistic. Then we find out the phase lags, actually the low energy band and the very high energy band, actually they are synchronized. In order to explain this, we propose that the very low energy photon detected by NICER come from the disk. And the disk and the jet are co-aligned together, they're actually precise together. So in this way, we could explain that the low energy photon and the very high energy photon, they actually come in phase together. And we also develop a technique we call we use the Hilbert-Horn transformation in order to understand this quasi-periodic oscillation. For example, that's from the data, we identified a mode that's in the middle, that's the quasi-periodic oscillation, actually two modes. One is the fundamental frequency, one is the higher, the first harmonic of the quasi-periodic oscillation. Then with this, we can do phase resolve. We can do phase resolve analysis of the QPO on its spectral properties. We find out that the spectral index for the gamma has a very strong correlation with the QPO phase. And if we still apply this model, that the jet and the co-aligned disk use this model, then we find out that the velocity actually within the jet is different. That is near the base of the jet, that's where the high energy photons are produced, the velocity is lower than at the top of the jet. That's where we have low energy photon, the velocity is higher. So it tells us within this compact accurate jet, we see the acceleration of the jet. It's basically the speed comes from 0.4, beta from 0.4, so all the way to 0.6 within this very short region. So we identified this as the acceleration region of the jet from the black hole accurate binaries. continue with the same source, the black hole active binary, during the very last episode of this re-brightening, then we correlated this with the radio data. And you can find out that the radio data comes behind the X-ray data. In particular, it falls behind the hard X-ray brightening of the last episode. So the interpretation of this is that the magnetically arrested disk was finally formed there. So in this, then with the corona is formed within the corona magnetic field, somehow it increased, then we have the radio emission, of course, in the form of a jet. Finally, I move on to a new mission that we hope that will be launched within the next few years. It's called the Enhanced X-ray Timing and Polarimetry Observatory. It will continue of a study of HXMT for black hole and neutron stars to understand extreme gravity, magnetism, and density. So on this satellite, we will carry 3 sets of instruments, and 1 set of instrument we call the SFA, spectroscopy focusing array, made of 6 X-ray telescopes with a total effective area more than 0.3 meters squared at 6 keV. We focus on the iron line science with this. Then we'll have 3 telescopes to make up the polarimetry focusing array. And with these 3 telescopes, the total effective area will be more than 350 square centimeters. Enrico will be very happy for this. We'll use the same, essentially the same instrument that you use on ICP. On improved version, I will show you. And this mission previously, currently it is still officially a China-Europe collaboration, but previously we also had 2 large European payload, large area detectors and wide field monitors. In this new configuration, we removed the 2 European instruments to overcome, to remove the programmatic uncertainty related to European participation. I think you understand that within the current geopolitical situation, it's a little bit hard to confirm the European contribution. So in this contribution, in this configuration, we don't have that. But however, we are still discussing with European agencies, trying to put back the European instrument. But nevertheless, even without the European instrument, with these configurations, and the mission will go forward. We have a launch time as early as 2028, but the administrative order is that it has to be before 2030. It has to be launched because that's the end of the next 5-year plan. So we have to finish this mission before that time. And in 2019, the China-European Consortium published a series of white papers on this mission. As you can see, on this one, we still have the LED instrument from Europe and WFM from Europe. But in the new configuration, at this moment, temporarily, we don't have that. We hope we can get this back. Now I quickly go on to the instrument we will have there. On the SFA, as you can see, it will be a mirror and with a focal length more than 5 meters, and we'll have 6 of this. And in the focal plane, we will be equipped with so-called the silicon drift detector arrays to allow high timing resolution and a good energy resolution. So that's the goal of this. Then another array, the mirror will be identical, but the focal plane will be the same as used on ICP. It's developed by our Italian colleagues. So this will have also a large effective area. So this is a comparison between EXTP and New Athena. And as you can see there, before 4 keV, New Athena is more powerful. Above 4 keV, we are more powerful because we are focused on the iron line science. On the PFA polarimetry, we will be something like between 5 and 7 of ICP in terms of effective area, okay? So therefore, with this, we can do spectral timing polarimetry on accreting black holes for sure. And you all know of that. We know we have now got a lot of results from ICP. And on neutron stars, our goal is trying to measure the mass and radial relationship, not for one, but for a dozen of neutron stars with a precision better than 10%, or even down to 5%. And on the vacuum polarization properties, and so far, ICP has detected a lot of polarization signals from accreting active pulsar and magnetar. Okay, but however, it's whether the predicted vacuum fluctuation have been detected. This is in debate. I think from the paper published by ICP team, they claim not yet. But as in the paper of Dong Lai, he said maybe this has been detected yet, but need confirmation from another mission. If we compare the focal plane detector we call XPO3 compared to what's being used on ICP, as you can see that essentially all the performance have been improved. This has already been developed by the colleague in Italy. But right now, due to some political problem, we may not be able to have the identical things in China. So we are also developing this in China. I will tell you later. We have a plan trying to duplicate this with the same technology to duplicate this, okay? And so this is a comparison on this. And once we have EACTP, we will be able to do exact simultaneous spectroscopy, timing, and phase resolved polarimetry. Currently, a lot of effort has been made to do simultaneous observation between ICP, NuSTAR, HXMT, the NASA, and all actual instruments. But however, as shown here, the exactly overlapped time fraction is on the order of only 10%. So it's not easy to coordinate simultaneous observation in space between different satellites. So once we have EACTP, this will be done by definition. That will be co-aligned with the same target. So EACTP in a nutshell is not only a larger version of ICP. It is larger, it's 5 to 7 times larger. But on the other hand, since we will also have a very powerful SFA, very large effect area, so we identify the phase of the QPO, then you can do the phase resolved polarimetry very easily with this. It's hopefully we can do this very soon. And this is a comparison between ICP plus another X-ray observatory and the EACTP. I don't want to go into detail. As you can see here, clearly, EACTP is more than a larger version of ICP. It has powerful functions. And I will quickly go to 2 other missions that I'm also being deeply involved right now. One is the Apollo 2 experiment on China's space station. This is a collaboration with Europe, and we will have 3 set of instruments. The Geneva people will contribute to the high energy polarimetry, and the 2 Chinese teams will contribute to the low energy polarimetry and the broadband spectroscopy detector. So this has already been selected and hopefully will be launched within the next 3 or 4 years. And the last mission I want to tell you is the HERT, is the cosmic ray experiment on China Space Station. I will show you here, this is how it will be worked. It will be delivered there, then will be installed on the space station with a larger robotic arm, then to work on China Space Station for the next 10 years or more. Hopefully this will be launched in 2027. This is also a collaboration with the European colleagues. That's what we have there. As you can see, it's a very complicated spectrum. It's a calorimeter in space. We'll be able to detect the cosmic rays with a direct measurement, and also it's a gamma ray Oscar monitor. So compare with other experiment, I only want to go to the last column and the acceptance. As you can see, is an order of the magnitude more than all the other previous missions in space. And we'll end with this. And since 2015 until for the next few years, China has launched a series of space missions in this area. And the last two, which are not, we have not started the final phase of mission, will be one heard for 2027, then the other one for 2029. I will stop here and thank you very much for your attention.
We thank you. And are there, oh, sorry, that's a question.
Which is the expectation in terms of angular resolution for the polarimeter? Because with the XP, we have these 30 arc seconds angular resolution, and we immediately find that something better could be very helpful.
Yeah, but over specification is 30 arc second also, 30 arc second. I'm not sure if we can do much better than that. The test is that with the mirrors, sometimes we can go to 25 arc second, but much better than that, we cannot do in China. So that's about what we can do, 30 arc second. This means it's very similar to XP in terms of imaging part. It's just larger and faster with a higher data rate, but otherwise it will be very similar. Okay, thank you.
Thank you. And time is running down. Oh,
Among the many things that you have done and you are doing, and we are all admiring, let me tell you that tomorrow we will present a data analysis of 221009.
Okay, yeah.
And I would like to attract your attention that we think in that source and other sources, we clearly identify, thanks to the Fermi satellite and LAT satellite, but Fermi satellite, vacuum polarization of overcritical field on very large scale, what we call the UPE. You will see that tomorrow, but what I can tell you today, that the result we will present tomorrow have been made thanks to the JCAMS instrument from your group.
Yeah, exactly.
And,
it's one of them, I show you.
And they have been crucial, and I hope tomorrow we will show you.
Okay, thank you. Thank you very much.
Congratulations.
Thank you very much. Okay.
thank you again. We have to go on. Next speaker is Klaus Lemmerzahl, talking testing gravity, quantum mechanics. Klaus, where you are coming?
Okay, thank you very much for the invitation. Okay, perfect. So I will talk about testing gravity and quantum mechanics. So this is the outline of the talk. First, I go into general relativity and then to quantum mechanics, and then I explore a bit the quantum gravity regime. So general relativity is somehow, or can be described as being based on an axiomatic approach by Ehlers-Pirani and Schild. So first we have the uniqueness of light propagation, and this then gives that you have a light construct, a geometry which is based on the structure of the light cones, and this has been tested with all the special relativity tests to a very high precision. The next issue then is the universality of free fall, or the weak equivalence principle. Everything falls in the gravitational field in the same way. The best test in the space has been done by the microscope mission, where the address parameter has been restricted to be smaller than 10 to minus 15. Next, we have to consider the point whether all particles move slower than the velocity of light. This is required by causality, and this has been tested in the lab to the accuracy of 10 to minus 6, and with the astrophysical experiments, astroparticles to 10 to minus 21. And the last point is that you need the uniqueness of timekeeping in gravity. So if you have two clocks and they moved different ways, then they, of course, show some effects. They have certain difference in time then, but they are still ticking at the same rate. And this is required this is related to the University of Quantum Mechanics, and it's called also local position invariance. This has been tested by comparison of clocks to an accuracy of 10 to minus 7. And if you take everything together, this is the so-called Einstein-Equins principle. And from that, we conclude that gravity is described by a curved Riemannian space-time. And here I go very quickly through two key experiments. So one is the microscope experiment testing the University of Free Fall. This was a French mission launched in 2016. And it's a small satellite. Here you see the emission scenario. So if you have two test masses and you compare whether the two test masses follow the same path. If they do not follow the same path, if the Equins principle is violated, then there will be a relative motion which has a certain periodicity. In order to avoid the periodicity of the orbit, one can additionally rotate the satellite, and this is the main issue here, that you can move the signal frequency away from the orbit frequency where you find most of the error input, and the result then is shown here. This is the last, the final result published at the end of 2022, and the result is that the Equins principle is fulfilled to the order 2 times 10 to minus 15. 2 orders of magnitude better than you could find on Earth. The next is the gravitational redshift. So you all know the gravity probe E experiment from 1978 with a hydrogen maser put on a rocket in a parabolic flight, and this then led to an estimate of the alpha parameter, which then tells you whether Newton is the coupling to the gravitational field is correct or not, restricting alpha to the order 10 to minus 4. And this was the orbit. And so you had one orbit with a height difference of 10,000 kilometers. In 2014, we had the launch of a Galileo 5 and 6, and they have been brought to the wrong orbit due to a malfunction of the Fregat upper stage of the Soyuz rocket. And they had, after some corrections, they still had a height difference 2 times a day of almost 9,000 kilometers. So every day you have an GPA, you have 2 GPA experiments. Yeah? So this was the idea. And then we applied for some funding and received that due to DLR and ESA. And so these are the orbits. So red is was the orbit after injection. Green is the target orbit. And at the end, we had the blue orbit. And with this 8,700 kilometer height difference. And this is, so the red line is a calculation of the gravitational redshift of the clocks in the varying height. And the blue crosses are the measured times. And so you see theory and experiment very nicely fit together. But of course, if you zoom in and go into the precision, then you have to make a lot of error corrections. And finally, we succeeded with that to improve the GPA experiment by a factor of 5. So we are now at the best test of the gravitational redshift with this Galileo satellite, and this also was a cover article of or PRL. We are also thinking whether it is possible to find a gravitomagnetic clock effect. So due to the rotation of the Earth, you have the gravitomagnetic field, and if two satellites move along different orbits, they accumulate different parts of the gravitomagnetic field, and this also should be shown in the clocks. We made some studies, first made some theoretical investigation. What could be the analytic description of the gravitomagnetic effect on the clocks if you have two different orbits? And this has been done with EVA. And then we also had a study here. So the comparison is that you have here, where is it? Here, you have to, so the J term is a gravitomagnetic effect, but there's a competing effect, this gravitoelectric part from the Newton potential, and so you have to be very precise with the Newton potential. So what you need is a knowledge of the orbit of the order of 40 micrometer. This is not so far away what you have today. You can determine the orbit of satellites by 1 centimeter. So one has to improve that by 1 to 2 orders of magnitude, and then we have access to this gravitomagnetic clock effect. If you now have, so this was just exploration of the gravitational fields. Now, of course, we need the field equation. There's no axiomatic approach to the field equation, so just stating it here. And what we also know is that if you have general relativity tells you what good clocks and good distance measurements are. This is given by the standard clock by Marzke-Wieler and by Volker Perlich. And this is related to the measurement of the distance by light rays and by postulating that the relative acceleration between two freely falling bodies does not depend on the velocity of the second body, then tells you that only a certain parameter class is possible, and this parameter class then constitutes a standard clock. So general relativity tells you what good clocks are. Then with these clocks, you can determine the distance, and also with light rays and falling particles, you can also define what rotation is. So we know everything very well from the theory, what clocks are, what is rotation, what is distance. The theory itself tells you what, how to measure these coordinates, and with these quantities, you then can test the theory. And we also have to check, of course, whether this geometric defined clock is also a good clock in the sense of the clocks we are using today. These are quantum clocks. These are the atomic clocks. And indeed, it has been shown by Parker and Pimentel that the modification of the frequency of a hydrogen atom is related to the curvature tensor times the square of the Bohr radius, and this is much too small on Earth to be tested. So this would give a relative frequency shift of 10 to minus 42. Only at the rim of a black hole near to the Schwarzschild radius you may see something, but this is not here on Earth. So that means everything is, that means that atomic clocks are also good clocks in the sense of the standard clocks. And with these clocks, we define what is the gravitational redshift, gravitational time delay, and the clock effect, and so on. So this is the scheme then of general relativity, whereby this time S is the standard time is given by the standard clock. And then we can have all the effects predicted by general relativity, effects on light rays, on orbit, on extended bodies, on clocks, and then also the gravitational waves. So the deviation of light is tested first by Eddington, and there will be improvements of that so today all the tests are somehow tested at the order of 10 to minus 4 in terms of the PPN parameters. With the Gaia, one could improve that by 2 to 3 orders of magnitude. Based on that, we have gravitational lensing and the shadow of black holes. Then we have the perihelion shift of Mercury, and then also the orbital effects, the Lense-Thirring effect, which has been seen by the Largus and Lares satellites, and they are approaching now the accuracy of 1%. Now they're at 5% approximately. And then we have these back correction effects of binary systems that they radiate gravitational waves. And this also has been tested with a very high precision. Extended bodies also feel the gravitomagnetic field if they are constituting a spin. And this has been seen by GPB experiment led by Francis Everett. Unfortunately, some experimental malfunction then reduced the accuracy so that they could confirm this to the order of 20%. And then we have this clock effect, the redshift I already talked about, then the gravitational time delay that near to a gravitational field, the light ray needs a bit more time than if there's no gravitational field, and then the gravitomagnetic clock effect. Okay, further tests are, and now I come to something new. This is the test whether Newton is true or not at large and small scales. There are many investigations on that from lunar laser ranging and Mars ranging and so on, but also on the smaller scales up to a micrometer. Nothing has been seen which shows a deviation from the Newton potential. Although within the standard model extension, a modification of this kind also has not been seen, and this has not been seen using atom interferometry on Earth and also not using lunar laser ranging. There's a second thing which is of principal interest. This is the question whether actio equal reactio is true or not. So if you have, for example, a two-body system, then each body possesses three masses: the inertial mass, the gravitational mass, and the active gravitational mass, which creates the gravitational field. And then if you write the binary system there, then you see these two equations with I is the inertial mass, P is the passive gravitational mass, and A is the active gravitational mass. And if you reduce this in terms of that you write this in the terms of the center of mass coordinates, then one can see that the center of mass coordinate will be accelerated if the ratio of active and passive gravitational masses is not the same. So this is a kind of equivalence of active and passive, or here a question of the equivalence of active and passive gravitational masses. In terms of the fixed two-body system, so we have the force between the first and the second body, and the force between the second and the first body. And if you add up, usually it will become zero. But if these active and passive masses are not the same, then this will not be zero. So the system then tries to accelerate. This is, of course, a violation of actio equal reactio, violation of energy conservation, or the violation of angular momentum conservation. One experiment has been carried through by Kreuzer in the group of Robert Dickey. So if we have two masses which have the same weight, that is the same passive gravitational mass, then we can ask whether they also have the same active gravitational mass by using such kind of torsion pendulum. So if the red mass has a stronger active gravitational mass or a stronger gravitational field, then we would see such a force. Yeah? If we interchange the masses, then we see that. And if you interchange the masses with the frequency of the resonance frequency of the pendulum, then this pendulum will start to oscillate, and this then led to an estimate of 10 to minus 5. We also can use the moon. The moon consists of two parts, an aluminum mantle and an iron core, and they are not concentric. The center of masses of aluminum and the iron have a distance. This distance is 2 kilometers approximately, and this then leads to an hypothetical force called along the S direction. A part is a horizontal force. This would lead to an acceleration of the velocity of the moon. The velocity of a higher velocity of the moon would lead to an increase of the distance between the moon and the Earth, and this can be measured very precisely with lunar laser ranging. And this has been first analyzed by Bartlett and van Buren in 1986 with an estimate of 10 to minus 12. This has been now improved by us through a new data analysis. the good point was that we had now not only 2 points of measurement, what they used, we had now 30,172 measured normal points for analyzing that. And we were very happy that we had data from Italy, from all the lunar laser ranging stations in Italy, and also from France, 3 from the US in Hawaii, Texas, and New Mexico, and the Wetzel station. So we had all the data from 52 years, and this, of course, was the major point here, that we could improve that. We also could use improved models of the moon and the ephemerides, and by fitting all the parameters. So we had 200 parameters which we could determine, including the Love numbers of the Earth and the Moon and so on. Then we could improve the equivalence of the active and passive masses by 2 orders of magnitude. So we are now at 10 to minus 14. So active, passive, and inertial masses are now equal to the order 10 to minus 14. Okay, another test, which is a new approach, is the test of the speed of gravity. If we have the Einstein equation, you see the Einstein equation, we can make a linearization, go into harmonic gauge, and then we define the mass density and the mass flux density of the matter part and the corresponding gravitational potentials phi and the vector potential AI. And with that, we can define gravitational field strength, the electrogravitational field strength and the magnetogravitational field strength. And with this, the Einstein equation reduced to the Maxwell type equations there. We can now reformulate that by introducing, instead of in the source equations, the E and the B, by introducing D and H, so the excitations, not the field strengths, by replacing the field strengths in terms of the excitations. That is, we have the D in terms of E, as shown here, and the H in terms of B. And with that, we get the upper equations. These are, if we now forget about what is where we come from, then these equations are the pre-metric Einstein equation. Yeah? We have an Einstein equation before we have any notion of metric. But we can derive from that with the definitions here, just with G and A and the mu G, that from that follows wave equations for the field strength with a velocity C graph, which is just G times mu G. Yeah? So this is then the velocity of gravity, just from these 2 constants, G, the gravitational constant, and then the mu G. And now we can do the following. We have the sources which determine the D and the H. From the D and the H, we determine the E and the B, the field strength. The field strength is that what is in the equation of motion, the weak field equation of motion, which has the form of the Lorentz force equation. And then we can determine the G from the force between 2 masses. And yesterday, for example, we had a nice talk in the experimental gravity session by King Lee of China, who had very nice new results. And the mu G can be measured by the Lense-Ting effect. And the Lense-Ting effect, as I told you, now approaches the accuracy of 1%. So that putting everything together, we cannot now say that with these 2 low velocity tests, we now can confirm that the speed of gravity is the speed of light to the order of 1%. Yeah? That is a new approach to testing the velocity of light. Okay, so this is just the scheme again. This is completely analogous to what we do in the Maxwell. You know, we can measure the Coulomb force, get then the electric permittivity, and then the Lorentz force getting the magnetic permeability. Both together gives the velocity of light, and in the same way we can do the analogous procedure in the weak gravity regime. Okay, so now we come to quantum mechanics. I don't know how much time I still have. 6, okay. So I will go very quickly through the postulates in 9, okay. So quantum mechanics now is based on our postulates. So one is that that we have a Hilbert space and that we have a quantization, which is related to the canonical formalism of the classical mechanics. Then we have, we can also say how arbitrary function in space-time can be quantized. This is with a while procedure. And the most important thing is, of course, the measurement process. Yes? The measurement process tells you if you want to measure a quantity A, then you have the corresponding operator, which we just constructed. We can define the eigenstates and the eigenvalues of this operator. And after a measurement of this operator, the quantum state is in one of these eigenstates and gives one of these eigenvalues. But we cannot say which eigenstate the system takes. Yeah? So this is open. Yeah? So this is completely undetermined. And yeah, this is the single measurement postulate. And the other postulate is then the Born interpretation that we can make a statistical statement that the probability that you find the quantum system in the state A is given by the scalar product between psi and A, and to square this. So this is the Born postulate. Okay, so this is a measurement process, the postulate regarding the measurement, and then the final postulate is the Schrödinger equation. And by this, we now have two types of dynamics, namely the Schrödinger equation and the measurement process. The measurement process is somehow discontinuous. People are not happy with that, but I think if you could understand the measurement process, then many quantum technologies will not be possible. Yeah, so it's of quite big advantage that the postulate works as it is. So consequences are interferences, Aronoff-Bohm effect, action accidents, which weigh information and all that. Then we have the quantization of the energy levels, uncertainty relation, entanglement is one, the no-cloning theorem, quantum teleportation, and of course, for example, quantum cryptography. And problems are the collapse of the wave function. In my opinion, this is too much classical thinking. I think this is not a valuable question. So we just should talk about measurements. The classical limit is of the same status. It is not really clear what is meant by that. Of course, we have the question of the 0-point energy and the cosmological constant. And we have the question how quantum matter creates gravity. These are reasonable questions. Yeah. Okay, and yeah, if you do measurements, then all measurements take place in two steps. First, you are doing the measurement. After the measurement, you have a superposition of all the states which are allowed by your observable operator. And then if you read out the experiment, then your knowledge collapses to one of these eigenstates. Yeah? And so we have 2 times a change of the entropy or the information of the system, but it's not clearly interpreted. So if we now want to test quantum mechanics, we have to have a theory which is more wider than what is given by the postulate. So the most simple thing is to modify the Schrödinger equation. We can take a non-local generalization of the Schrödinger equation, higher order differentiation, or we take non-linear modifications or add non-Hermitian terms. Everything has been done. So for example, Volker Perlich and Jakov Itin and I have discussed the Finslerian modification of the Schrödinger equation given by such a kinetic term. And this then leads to effects which are not there if you compare this to, say, a standard Euclidean Hamiltonian. Or once I also did some discussion on higher order differentiation in time. This also gives modified dispersion relations and different energy levels in for example, in the cavities or in the hydrogen atom, and this can be excluded by experiment, for example. There have been many experiments searching for non-linearities in quantum mechanics, and there were also some experiments discussing, or some theory, some investigations discussing experiment in terms of adding non-Hermitian term, in particular in the context of the search of quantum gravity. But nothing has been found. Quantum mechanics is correct according to all experiments what we have done. Then one can talk about quantization. There have been many attempts to modify the commutator relations, and this then, of course, leads to modified uncertainty relations, but also to a modified representation of the momentum operator in terms of the operator which is commutative. And this then means that we have a Hamilton operator for this modified commutator relation, which looks like the usual Hamilton operator, instead that we have a momentum operator which is non-local in the original quantity. So this is just equivalent to a modified Schrödinger equation. What can be done is also to derive the modified Heisenberg equation. This leads to a modification which depends on the mass and which is interpreted as violation of the equivalence principle. So there might be possibilities, or in many cases, the changes of theories then are not compatible with the standard assumptions of general relativity. Okay, the measurement process. There's this Girardi, Rimini, Webner. How much? I have to stop. Okay. I just want to here. This is the discussion of the Born postulate carried out by Sorkin, that if a P12 is, if you have two slits open and P1 just one slit open, then in classical mechanics there is P12 is the same as P1 plus P2. In quantum mechanics, the interference pattern is there, but the three slit gives zero, and then we could think about a modified quantum theory, a more generalized quantum theory, in order to allow even the 3-point interferences. This has very nice mathematical structures, and this also has been done in the theory where we have an experiment with 3 single slits, 3 experiments with single slits, and 3 experiments with 2 slits, and 1 experiment with the 3 slits, adding up things, and what comes out is a 0. So we are not at the second order quantum level. We are still at the first order. And one also can think about generalizing this Born postulate in terms of, so this is the usual, and a generalization is just, if you think at Finster, this might be also a probability for measuring a state. This, of course, is no longer U1 symmetric, but this then would imply that the coupling to electromagnetism would change. But and I think it should be more common to test these somehow crazy generalizations of quantum mechanics, and also might think that whether the probability is independent of the particle, or not independent of the particle, that if you have a measurement of an electron, you have to use another probability measure than if you measure something on the proton. So this is then a kind of equivalence principle on the quantum domain. So we should have a new culture for questioning quantum mechanics in order to have more experiments in quantum mechanics. So in the general relativity, you have this PPN formalism, you have these higher order things, we have momentum space modification and all that. And here we have practically nothing. So we should have more tests in quantum mechanics. So this is my main statement, that we should be open to have more tests in quantum mechanics. We should be we should modify quantum mechanics as we can and suggest this to the experimentalists. Okay, thank you very much.
Thank you, Klaus. Time is running down. Is there an urgent question? Only an urgent question. Otherwise, okay. A short and urgent question. Yeah. Okay, sorry.
So if the test to the general relativity Einstein theory without involve intrinsic spin, like electron or lepton quarks, only for rotating spin, so maybe it's then no new effect. You will find this all okay. That's one comment. Second comment for the quantum mechanics. Quantum mechanics, from quantum field theory point of view, quantum mechanics is effective description or linearized equation. But actually, we know from quantum field theory, the interaction is no linear. So the test is, how to say, is maybe not perfect.
Is it really urgent?
I sympathize with the statement of William. This meeting, I think, will be historical, and remember, and there has been one other concept which sooner or later you will have to consider: the difference between the mass and the irreducible mass. And both of them contribute to the energy. But the dynamic of the system within an ergosphere cannot be treated without irreducible mass, just by ballistic method. But it's too early to discuss the detail. Let's have the material presented here settle down a moment.
Okay. Okay, thanks, Klaus. Next speaker is Manfred Lindner. You are here. Hunting dark matter.
Okay, so this presentation is about hunting dark matter with the xenon experiments. It's quite a different community usually, so I try to explain what we do and why we do, and then what the results are. Just a quick reminder on the fact that there's many evidences for dark matter, and I assume that Katie Fries in her presentation will give a lot of details, and this is just a flasher to remind you there's lots of experiments which are everyone talk by itself. The overall situation is the following then. We know that about 5% of the universe is what we know, while the rest is unknown, an unknown form of matter or something else that's going on here. And of course, we can decompose it. There's also known things like radiation, chemical elements, stars, gas, and etc. On the lower side, there's neutrinos. We know that neutrinos exist, cosmological neutrinos, so they are in some sense a component of the dark matter of the universe. There are black holes, normal black holes that we do exist, that are a tiny fraction in the mass balance there. And of course, there could be primordial black holes. And then the leftover part is dark matter, which is about 26%, and dark energy, which is about 68%. I'm not going to talk about dark energy because that's a problem that in my mind goes even beyond quantum field theory. It's a conceptual problem. But it's always important to remind ourselves that we're talking about effects on top of something else that's even bigger. So that might have some risks in it that one could discuss and come back. But I don't have time for this today. If you think of where the solution is, then there's two main routes. One route is to say maybe gravity is the culprit, and the other side is to say maybe it's particle physics. Both sides could eventually be it. On the gravity side, there's what's been called modified gravity. MOND was one of them. A simple, in some sense, one parameter modification of gravity. And given now all the facts, it's sort of say not surprising that one fails to explain all those facts, right? I would say it mostly fails by now. There's some people defend it still, but I think it fails. But that doesn't mean that gravity couldn't be the culprit. The question eventually could be that the Einstein principle that Einstein observed is an effective observation and it's built in the theory, but there could be a level of precision where it fails, where some even more complex theories have to be looked at. And that's something where some people work on, and they will not discuss that here. The other element in gravity is black holes. Of course, today's black holes, which are a tiny component of the matter balance. And of course, a suitable population in terms of mass and number of primordial black holes could be also involved. The other side is particle physics, and there's two categories. One is what I call beyond the standard model of physics motivated. The standard model of particle physics has known problems, and trying to solve them, one ends up with expanded theories with new particles. There's the neutrino sector, and we know that neutrinos are already a component of the dark matter, normal neutrinos. There's arguments for new so-called stereo neutrinos. There's WIMPs. The most well-known is the neutrino in supersymmetric expansions, but some more general terminology. There's axions connected to a strong CP problem. So these are the BSM-motivated candidates. And then there's other candidates which people find interesting from a generic theory expansion of the standard model. And again, WIMPs show up. They're so-called dark photons or axion-like particles or other new particles, which nicely could be a dark matter that you look for. I would personally distinguish between two main categories here. One, which is thermal production. That's the WIMP miracle in some sense. If you have a big bang and put this new particle in and run the equations, and you get without much ado with the abundance that you want, it smells like the right thing that's connected. That's been called WIMP miracle for whatever reason. The other route is, of course, to give up on that. We have some particles produced that react, decay, etc. And then we're talking about the leftover decay products today. Both routes are equally good, but the one that shows up on both sides, the WIMP, that's why this has been followed by most experiments and by many theorists. A word on primordial black holes, the discussion usually goes this. There's different sizes, small primordial black holes on the left side. They are too small, they would evaporate by now, they would have been gone. Mid-size or larger size black holes would accrete, would become bigger. And then if you look at what we have in terms of experimental input, this is one version of that. Then there's a gap left on here where you could actually saturate the dark matter with primordial black holes. If you don't saturate, there's still an option, so say to use primordial black holes to explain part of the dark matter. So maybe they are 1% like neutrinos, or maybe they are everything. That's the option we have. Personally, I find it a little bit amazing, so to say, because that middle part which is allowed is the part which is so to say depleted. The smaller ones evaporate, the bigger ones get bigger. It's actually where the survival probability for a primordial black hole is lowest, so to say. Next is the particle physics side. It spans over really many orders of magnitude. There's lots of candidates theorists come up with. And there's two halves. There's the left side, which is wave-like. They're so low in mass that their wavelength is so long that you should think of these particles as waves, where you do like antennas and things like that. And the right side is more particle-like, so I see interactions of individual particles. I'll focus on the right side, and mostly on the WIMP or WIMP-like, etc. direction, but also others that are included. Next, how would you detect such a particle? You can essentially, under some minor assumptions, write down this diagram where two standard model particles react with two dark matter particles. And you can read the diagram in different directions. You can read it top down. That's the area of colliders. You take particles and collide them like at the LHC. You may detect in this way a new particle that has all the features of the dark matter that you're looking for. But how can you be sure that's dark matter? You may produce a particle that leaves your detector and decays outside, so it's not stable. And even if it were stable, you can prove the abundance in the universe. It may be a particle like the neutrino, which is a percent or something like that of the dark matter you're looking for. But it's of course a very interesting way to go, and that's what people do, and should of course be done. The other one is indirect detection, where essentially look in space in some places where dark matter annihilates, read the diagram bottom up, and produce standard model particles. So you look especially at areas where there's more dark matter. More dark matter is usually the galactic center, the sun, places like that. The problem with that is that in these areas there's also uncertainties, how much you know what's going on there. So it's very often the problem to identify and make sure that you see it's not some standard process that you should subtract. Of course, it's also important, is done and should be done. The third method is to read the diagram from left to right. to have dark matter from the universe come in and hit your standard particles here. Means put up a detector. And of course, there's some uncertainties also, but that's what I will follow from now on. That's in the Xenon program. So the idea is that there's a wind coming from the fact that the Earth moves, the solar system moves, and they're essentially plowing through the galaxy and see the WIMPs, which is a ship, they're coming towards us from one specific direction. That means there's a minimum in December and a maximum in June. There's some modulation over time, and there's some uncertainties in the halo modeling shown in the upper right plot here. If you have enough statistics, then you will see this effect by a change in the spectrum, because if you move towards the wind, then there's more energetic events. When you move away, it's less energetic events. So at some point, this will be very interesting. At the beginning, of course, you would be happy to see the rate only before you look in these details. Next, how you detect the WIMP. The rate in your detector is essentially a convolution of three elements. First of all, there's the detector, the size of the detector, the threshold, etc., and so on. There's the astrophysics, that's the assumptions or modeling of the wind that goes in. And there's the last part, the blue part, which is particle physics, the microscopic reactions of the WIMPs as they enter the detector and scatter to make them visible. Here there's three different examples for nuclear recourse, the axial vector couplings, the scalar couplings, the vector-like couplings, and they're called spin-dependent or spin-independent. The point is that spin-independent interactions are coherent scattering, so they're proportional to the atomic number A squared. So the spin-independent process, like the lower ones, are much, much stronger than the other ones, which are spin-dependent. That's why spin-independent is always the race, the benchmark, etc. Then the question is where to go, where to search. That's like in Middle Ages when you had white spots on the map and to build a ship, and the question was how big is the ship to be, where to sail, etc. And that's essentially this plot. It's the cross section against the WIMP mass, taking the argument that the WIMP is connected somehow to the promise of the standard model, end up with particle masses in that range, typically, let's say 10 GeV to 1000 GeV. That's a typical range from year to year. And the cross section is something not random. It's something very generic. If you take quantum mechanics, the size of the particles to de Broglie is like squared essentially. And then you multiply the cross section with the coupling. If you have parameters of order 1 or maybe 0.1 or 0.01 squared, not fine-tuned, a coupling order 1 and the area, end up with cross sections which are in a range of 10 to the minus 42 to 10 to the minus 49 square centimeters. So that's this gray area where vanilla WIMP should sit. And if you look in the literature and theory papers, you find they look more complex because that's the detail of the theory. But the argument that this is the area where the signal should sit is generic. So it's very important to build a ship, so to say, that can sail far enough and penetrate that area. That's what the people in the community have been pushing for. Next, how do you detect? Well, essentially, it's playing billiard with invisible balls. That's the comparison people make. The WIMP is invisible. You put some balls on the table and watch what happens to them. So there's a WIMP coming in, hitting a target, and that produces three kinds of signals. There's ionization, light, and heat produced. Then, of course, you have a detector, and you have to pick up the signals. You can pick up either one of them. And picking up either one of them means that you're not seeing enough because there's some backgrounds that look the same. So the idea is to combine different signals to be more selective for background. And that's done with different technologies shown here. And I will talk about the liquid xenon out because that's the one which has been extremely successful and will be very successful in the years to come. That's where ionization of light is both measured and detected and used to suppress backgrounds. This led to the Xenon collaboration. It's been our collaboration with about 200 people in 12 countries, 29 institutions. Started with a small group of a handful of people and it's been growing, and the growth essentially is just showing the success of the experiment, but also the complexity of the experiment that we're doing. The essential strategy is to make the detector bigger and bigger, and at the same time cleaner and cleaner. We start off with, let's say, a 5 kilogram detector in Xenon 10, and then environmental rate, it's 10,000 decays per, etc. That's typical environment. Everybody that sits here is about 5,000 decays per second in your body, mostly potassium 40, 5,000 per second. And that goes up from 5 kilograms to now to a total mass of 10, almost 10 tons, and the fiducial volume that's smaller. And the background has gone to a very tiny number. That's really 10 to the 5 times cleaner than the environment, right? It's an art to get materials as clean, to select them, keep them clean, etc. And this combination of getting bigger and at the same time cleaner, that's the power of the technique. And that has led to 6 orders of magnitude sensitivity increase over the last decade or so, which is quite tremendous. The way it works is actually, one thing is the so-called dual phase TPCs. They're very powerful devices, and they work like as follows. It's a container with liquid xenon, the dark blue, some gases, xenon, the light blue, and PMTs, light sensors on top and bottom, and everything made from very clean materials. And if a wind comes in and scatters, it produces a first light signal from shaking a xenon atom, and this light signal is detected as a pulse called S1 in our language. Then the charges which are liberated are drifted by an electric field that's applied upward, and when they move out of the liquid in the gas phase, they produce a second light signal, S2, like a proportional chamber. And that second S2 signal is then what's seen. These two signals have a drift time. The drift time allows you to say how deep it was in the Z coordinate, and the light sensors on top and bottom allow you to reconstruct the XY coordinate of the event. That means you have a very excellent, precise three-dimensional position reconstruction of the event that you saw. It's very good. Then, even though your detector is made from clean material, you're still finding background. And the way to do that is what's called fiducialization. You essentially see that there's still backgrounds, and what you do is you take with your computer the outer part of the detector. Those events you throw away, essentially. You take this extra layer of xenon on the outside as extra shielding and just keep the inner part to maximize signal to noise. You do that before you analyze your data, so it's for Monte Carlo, and then you open up the box. There's some events in the signal region, and then even less in the background. And then you have these S1, S2 signals, and depending on how this cat on what is cat on, there's difference. There's what's this S1, S2 ratio is important. If you look at the energy and the ratio of S1, S2, there's electron-like events, which are the blue ones on the upper side, while nuclear recoils, the red ones on the lower side. So there's a very characteristic feature, the position that you can use to fiducialize the energy details of the S1, S2 event, and that's very powerful, extremely powerful to subtract backgrounds to enormous amount. Backgrounds are actually your main enemy, so to say. You have to avoid all sorts of backgrounds going from your environment to orders of magnitude lower. So what you do is you go essentially into what's called material selection. You screen material that you get carefully, make sure that literally every screw is clean. You also do so-called radon screening, there's radon emanation, etc. Avoid any sort of nuclear background. I could give you an hour talk on this now. In the end, the detector is a graded shielding. You go deep underground to use the mountain above you in Gran Sasso here to shield you from the cosmic rays. Use a Vita system around, means you build a water tank with clean water around it, with PMTs to Vita muons. You put even neutron Vita around it, etc., and so on. And then you clean the liquefied xenon by cryogenic distillation even further down there. And then in the end, when you analyze this pulse, you pulse check this creation to look at this S1, S2 pulses. But then, of course, you're looking for the WIMPs that come in, but then there's backgrounds, neutrons and gammas from the rock, for example, around you, alpha, betas, and gamma from the material that you lose, neutrinos, which are generated cosmogenic, and last but not least, the sun is a background, because the sun is sending neutrinos, and the neutrinos just go through the Earth as if the Earth wouldn't be there. And if axions exist, there must be axions coming from the sun. You can think of background or signal as what you prefer. That's then the realization. The xenon detectors have been operated in Gran Sasso, not far from here. And over time, we have gone from this small detector, which was called Xenon 10, to what's now called Xenon N-ton, which is running now, actually data taking. We're just releasing new results. Actually, this week, there's a conference at Gran Sasso where I talk here. It's been going bigger and bigger and cleaner, as I said before. But that's really the challenge. There's many, many details about making this TPC cleaner and bigger, make it work, and at the same time to have all the shielding, etc., improved as time goes by. This is how it looks. It's one of the holes in Grand Zastor, hole B. This is also a big water tank. The image on the outside shows the TPC that's inside, and this is the usual service building with a gradual distillation storage system, data acquisition system, and cleaning system, etc. We achieved quite some remarkable background conditions shown here. This is events now per ton and year. So numbers here are like what you have per second a kilogram in your body, right? That's what it is. And this shows xenon 1 ton, and now down there, the gray band is xenon n ton. This is really an ultra-low background of 16 events per ton and year kV, which is really important to have the best possible signal. It's quite an achievement. Shown also are some of our competing experiments in other places, which get similar results, but we, I think, obtained the best result here. Then some results. One channel is to look at electronic recoils. These are this S1, S2 space, these green upper events, upper type events. And you see them here, they scatter. By using the fact that there's essentially energy conservation, meaning that the S1 and S2 pulse together must add up to the energy that's deposited, you can transfer these scattered events here to a well-defined energy. Up there, this brownish picture. And when we did that in xenon 1 ton, we saw this curve in the lower left, where the expected signal is reddish curve here is what's expected, and the data points for xenon 1 ton showed an excess at low energy. This excess created a lot of excitement because it could have been the onset of signal. There were hundreds of theory papers written to explain that, etc. We were cautious. We said it could be some new background, it could be statistics or some new physics, etc. And of course, when we continued, one of the first things to do was to look in xenon n ton at the same part that's now down there with more radio purity, etc. A different exposure. You get this line down there, means this excess is gone, which now translates into limits and all sort of new physics that people invented that cannot be there. Another one is the limit on spin independent with nucleon cross-section. The limit here is 2.6 times 10 to the minus 47 square centimeters. If you remember the plot, it's deep in the Parmer space where you could see a signal already, which is interesting, and that's also these curves up there, that etc. There's also in the community discussion, let's say, going on, different experiments have similar experiments. We are competing, and it was when somebody comes up with a new data, then you're catching up, etc. and so on. There's one important point. I think there's some difference in these kind of lines, which have to do with the fact how the analysis is done, how statistics is done, how event selection is done. That means we have to get together in the community and discuss more to get the same language, etc. In all, I would say that these competing experiments have obtained similar sensitivities. Depending on time, the race is going on forward and backward. If you look at the total picture, then this is from the particle data group 24. Then this is what we have. So there's these color lines which show where we are. The blue line is this neutrino background at the bottom there, and we're getting deeper and deeper in this Parmer space. A long scale, so there's still quite some space to go, but we are, in some sense, these big ships that we're building are sailing in the territory where every moment a signal could pop up. It's actually interesting to see what happens once you go into this neutrino signal, neutrino background. Then you can be unhappy because then you're so blinded by neutrinos. But that simply means that you're doing neutrino physics. You look at the solar neutrinos, atmospheric neutrinos, and the neutrino physics is done for free. Next is limit on spin-dependent nucleon cross-sections. They say they are not coherent. That's why they are weaker than the other ones. For a neutron-only coupling or for proton-only coupling, you get this kind of limits. There's more to be done. There's limits on other things like solar axions, neutrino magnetic moments, axion-like particles, and dark photons. I have no time to discuss this in detail. It's just to show you that these kind of detectors are sensitive to many things that you can think of and speculate about and either find it or set limits. It's not only limit setting. Sometimes you find something interesting, surprising. And that was the discovery of double electron capture of xenon 124. Which actually gave us the cover page of Nature. It's actually a standard model process. It's not something unexpected, but it's just that it's extremely rare. The point is it's the fact that the process that two electrons in the atom are swallowed by the nucleus by two beta reactions at the same time, happening at the same time. such that suddenly the charge of the nucleus changes by 2 units, while the electrons are still there going around, and realize, oh, the charge of the nucleus changed, the atom, right? And that, of course, leads to the consequence that the atomic relaxation goes in. There's Auger, gammas, etc., emitted, and so on. And that's so say just showing that the nucleus changed charge by 2 units, and you see it. The neutrinos escape unseen, of course. It's a second-order weak effect in particle physics language. It's the simultaneous exchange of 2 double bosons at the same time, which is rare squared, so to say. And if you look at the lifetime, you get this number here, which is 10 to the 22 years. It's 1 trillion times the age of the universe. It's mind-boggling to see that we talk about processes which take, as a particle reaction, 1 trillion times the age of the universe. It's very nice. Of course, it's not unexpected in some sense because it is a standard model process. Now, from here, the question comes how to continue in the future. And this is actually Moore's law in this field. This is the cross-section sensitivity as a function of time, where you see again what I said before, that with xenon, we made orders of magnitude. There's also detectors based on argon, the red points, they also move. But xenon has been leading the field, so to say. And as you can see, there's more potential. And of course, it's very tempting and obvious to follow that route and continue and see how far you can push that. That means the next step is something similar but bigger. It's called XLZD. Would be something like 60-ton fiducial. The TPC would only 3 meters. It's not that big because it's a three-dimensional object at this scale. And there's another factor 10 in the background, which is partly or mostly already obtained by now. It's not crazy, it's doable, etc. And so the consequence was that the collaborations partly merge, the xenon collaboration and the LZ collaboration, which is US, UK based, etc., and Darwin, which is mostly xenon, merged together into a new consortium that's called XLZD to work together and build such a detector. There's a lot of ongoing R&D, not that we only dream of it, it's really happening. The TPC scaling work is ongoing. There's what's called a xenoscope, the drift length, pancake, wider grids, PMTs and photosensors developments, high voltage and grids, alternative designs, lots of things happening, so say. Background mitigation, how you further make this cleaner, etc., how to avoid radon emission, all these things, etc. What's been proposed in this context is an upgrade of xenon in Hall B. It's shown here as a photomontage, so say. They have an intermediate step built in there, which is an upgrade which tests many of the components that you would need. So it's really not just jumping there, it's really demonstrating that this step can be done. And that's actually happening and is a very nice way to go. Instead of jumping with a big detector in a new territory, you step by step validate that it works. The XLSD could have different locations in Grand Sasso, the Pyrrole C, for example, shown here, where there's, let's say, the dark side and legend in between could be Darwin or XLSD detector would fit there. There's different locations being discussed besides Grand Sasso, it could be Pulsars, Surf, Commerce Lab, that's ongoing discussion, and has to be seen which laboratory actually is most attractive and most willing to go that route. So, oops, there's something frustrating with that slide. Oh, yeah, that's bad, because that's, so say, a plot that shows what an XLDC detector could do physics-wise. Don't know, can you reload maybe this page? Is something wrong? Can you maybe take the PDF then or something to get the slide? Just switch to the PDF version. I don't know why it doesn't work. Yeah. So the point is that this future detector is even more sensitive, and this opens up a number of physics channels that so far are there. So even though, yeah, just go to the almost to the other end. Yeah, one more. Yeah, here we go. So it's actually what you build then if you go to the next iteration is an observatory, because there's really a number of physics cases popping up simultaneously. First of all, there's of course WIMP dark matter or alternative forms of dark matter, which continue with more sensitivity, pushing all the way down to what's called neutrino floor. Of course, then there's other dark matter forms like dark photons, axion-like particles, Planck mass dark matter, which also can be looked for. Next one is the neutrino nature is an issue, because there's in, say, 50 tons of xenon or so, or 60 tons, There's a few tons of xenon-136 natural isotope, and xenon-136 is a double beta isotope. So you do a double beta experiments with this kind of detector. So you can look for neutrinos, double beta decay, double electron capture, and magnetic moment of neutrinos, all of them being new physics beyond the standard model. You can do cosmic ray physics with this kind of detector. On the other side, the sun, by seeing solar neutrinos with coherent scattering with more precision, we can turn the crank around and study both the sun as a standard star, understand it better, the boron 8 flux, and you can also use it to understand if there's new neutrino interactions, so-called NSI operators, magnetic moments, and things like that, which people talk about. Last but not least, if a supernova goes off, they will, of course, would be seen in such a detector, and combined with other detectors would be a tremendous input for this kind of physics. So I hope this convinces you that this route is promising and should be followed. Let me conclude then. Next slide, please. Can I go to the next slide? Yeah, so let me conclude. So dark matter is still a very attractive and diverse field. There's still, as I outlined at the beginning, there's many options that we talk about, and all of them should be taken serious. All methods to go after should be taken. It could be new particles or gravitation effects or both. Both sides contribute already a bit. We know that neutrinos contribute, normal neutrinos. We know that there is black holes at some level. So there's some tiny components known. What's the rest? I focused on particle physics, and even then there's many theoretical options which I didn't cover. I focused on particle-like candidates, where then there's direct detection methods by LHC indirect detection and direct detection. And I focused then on direct detection because that's seeing the direct component of the dark matter in the universe. And then I showed you that we obtained with this xenon technology orders of magnitude by scaling the TPC and the background in the last years. There's more potential to go, etc. I showed you some limits, and I hope to convince to the end that this route is not ending yet. There's much more to come. Thank you very much.
We thank you very much, and I open a short discussion. There's a question.
I have two comments. One of them is, I just want to point out, in the United States, the Department of Energy in its Cosmic Frontier has prioritized this as one of its missions. So the US is putting money in. And the second comment is about the Dama experiment, also located an hour from here in the Gran Sasso Tunnel, right next to Xenon, the Xenon experiment. And they have a 14 sigma result over 20 years, I don't know, of annual modulation of the signal, exactly as we predicted that it would peak, as you said, in June, the signal, and a minimum in December as the Earth goes around the sun, changing the relative velocity with the WIMP wind. Now, the thing that's strange about the experiment is that disappoints people is that they're not releasing their data to everybody else. And also the question is, how do you compare to the Xenon experiments? In the plots you showed, you're assuming a particular interaction that's been independent, and definitely Dama is ruled out even by itself. That's not what it is, but we don't know. How do you compare apples and oranges? Sodium iodide, which is what Dama's made of, versus xenon. These are different materials. So the key is to have more other experiments. There are now 5 of them also using sodium iodide. And I know that today at the International Dark Matter meeting, the cosine experiment in Korea, which is also made of the same material as Dama, is announcing some result anyway. So we still don't know the Dama situation. It's in flux.
Yeah, thank you. There's 2 important comments. First of all, the P5 has said that Generation 3 is on the roadmap, and we actually discuss it with our American colleagues, and we are moving. It's great. Second point is an interesting story. I didn't mention it because it's quite controversial, but it's many sigma. The question. So the second point is, so there's the Dama result is quite controversial. So for one thing, could be a different interaction. So the one speculation was that Dama is testing so-called leptophilic dark matter which only couples to leptons, while these are nuclear recoils, you wouldn't see them. But now this is excluded because you can also do an electron scattering, right? People look at that. And there's been a list of arguments people made, what kind of nuclear background could be there. It's fair to say none of them explains what Dama sees. That's the fair thing. But there's one thing, the cosine expert, the Korean expert I mentioned, they showed already that the binning, how they bin the annual data makes a difference. There's a background that's slowly decaying, And the atomic people bin it, so say, by the year, such that the binning, so say, can pick up something. So it'll be interesting what they show, if that persists or goes away. It's an open issue, and we should look at it, etc. But there's a race for ideas. On the other hand, so say, I don't know of any convincing particle physics model that would reconcile that result with everything else. So clearly there is a modulation of something, but it's a big mystery.
Okay. Thank you. And we should stop now here. We can shift all the discussions to later. And I'd like to thank you again. And come to the next presentation. Center's always here, Blake Sherwin. Please start your presentation.
All right, so thanks very much for the opportunity to speak here today. I'm going to be talking about what I think is a very important question, namely, do we understand the growth of cosmic structure? And I'll discuss what we can learn about this question from new CMB lensing measurements with the Atacama Cosmology Telescope. Let me start, though, with some background to this area. I'm sure everyone here knows, and we've heard in the previous talk, that even though we've seen an enormous amount of visible matter in stars and gas and galaxies, this is less than 20% of the mass, and the vast majority of mass in our universe is made up of invisible dark matter, which underlies the distribution of galaxies. Now, we believe at this point that we have a pretty good understanding of how this dark matter dominated large-scale structure forms. And the standard idea is that the small initial density perturbations are set up in the very early universe, and then over billions of years, these grow due to gravity, forming our large-scale structure. So the interesting thing about this is that how exactly the cosmic structure grows with time is very, very sensitive to the composition of the universe, to the properties of the density perturbations, and even to our theory of gravity. And so therefore, structure growth with time is an extremely powerful probe of new physics. And this is why we would like to be able to use gravitational lensing to map out the distribution of mass at different times, because how the mass is distributed, and in particular, how large it's grown to be today, contains a wealth of information about some of the key questions in cosmology, such as, what are the properties of dark energy and dark matter? What are the masses of neutrinos? And, is GR our correct theory? Now, if we want to make this more quantitative, we can introduce a key parameter that I'll be referencing over and over today, a parameter called sigma 8, which tells you the amplitude of density fluctuations today. How large are these structures today? More precisely, it's the root mean square density fluctuation on 8 megaparsec spheres, if you smooth the mass distribution on that scale. Okay, so let's just say I would like to use these gravitational lensing measurements of the mass distribution and of the growth of structure to look for some new physics. How do I proceed? Well, the first way of proceeding is to come up with a particular model. Say I have my favorite dark energy model, and I can go and look for evidence for this. But I can also proceed in a more general and agnostic way and just ask the question at increasing precision, does large-scale structure grow as our standard cosmology predicts? And a version of this sort of agnostic test of structure formation with the longest redshift lever arm, and therefore, in some sense, the most power, is the following. I can fit a standard cosmological model, that is a lambda CDM model, to CMB observations at the earliest times that we have access to, at redshift 1100. And then I can predict over many billions of years how structure forms all the way down to redshift 0 to today. And in particular, I can predict the value of sigma 8 that I should get today. I can then compare this predicted value of sigma 8 with a direct measurement of sigma 8 that I get from lensing measurements of the mass distribution at late times in order to stress test my cosmological model. So this is a generally very powerful and interesting thing to do, and we're going to want to do this stress test at increasingly high precision going forward. But in recent years, there's even more motivation to focus on this kind of consistency test because there are hints that something might be going wrong. And this has become known as the sort of sigma 8 or S8 tension. And S8 is, you can think of it basically interchangeably as with sigma 8, it's closely related. It's just sigma 8 times the square root of the matter density, because this is what lensing constrains best. So this plot really summarizes the S8 tension, the so-called S8 tension. It's a tension between, on the one hand, these green points on the top right, which are the predicted values based on a lambda CDM fit to early time CMB observations, mostly with Planck. And then on the other hand, you have in blue these kind of direct low redshift measurements from galaxy surveys and mostly galaxy lensing. Now, the interesting thing is that, even though each of these probes on their own is just 2 to 3 sigma low, and even though they're not all totally independent, different probes seem to be coming in low at the 2 to 3 sigma level. So the question is, what is going on here? Are we just making a big deal out of fluctuations? Is this, a sign that there are systematics in one or many of these data sets that we've just neglected or underestimated? Or, the most interesting possibility is, of course, that this is a first sign that lambda CDM is breaking down, and then there's some new physics explaining this tension. So in this talk, I'll focus on how our new CMB lensing measurements with ACT can, to some extent, help clarify this situation. All right, let me remind you and explain to you a little bit about CMB gravitational lensing. I'm sure this audience knows everything about gravitational lensing, the fact that all mass, including dark matter, deflects light that passes by. But in this talk, I'll focus on the lensing of kind of a special source of light, the cosmic microwave background, the afterglow of the hot Big Bang. And I'm sure everyone has seen these beautiful images like this one from the Planck satellite of the CMB. The CMB is a great source for studying lensing, and that's first of all because we understand it extremely well. We know exactly what redshift it comes from. We can use simple linear theory to understand these perturbations. But it also is kind of the most distant source of light that we can see, and it lies behind, all the mass that we can observe. All right, so what happens then as the CMB photons travel through our universe is they're gravitationally lensed or deflected by the entire large-scale mass distribution through which they pass. And this leads to a net remapping of the CMB patterns that we see today in our experiments. Now, the real effect is very small. It's just moving around these fluctuations by a few arc minutes. And so I like to show a really, really exaggerated cartoon picture so that you can get some intuition. So here's a 10 by 10 degree cutout of the CMB sky with lensing switched off. And now I'm going to, just to illustrate things, place a hugely exaggerated blob of dark matter in front of the CMB picture. And what does it do? Well, it lenses the background CMB. And the point is that you can see this very clearly in this exaggerated picture by eye because the CMB fluctuations are magnified and sheared in the direction of this dark matter. And that's the signature we're sort of looking for. All right, let's make this more quantitative. We can describe this sort of CMB lensing process with an observable, the lensing potential phi. Okay, and this is defined by the following statement: the gradient of phi describes this lensing remapping on the sky. So basically, grad phi points from the direction in which a CMB photon was originally emitted to the direction in which you receive it. All right, so I said that the lensing potential is an observable, but how can we actually measure this? How can we determine this lensing field? All right, so let me explain what we actually do, and then I'll try to give some intuition. So what we actually do is we run an algorithm called a quadratic estimator. The idea here is that we take a harmonic transform of the CMB map to get the mode T of L, and then we perform an integral over different pairs of modes. And that gives us an estimate of our lensing. Now, that's not particularly intuitive, so you can understand, at least in some limit, the physics of what this is doing pretty simply. So basically, what this estimator is doing is it's locally measuring the CMB power spectrum in little small regions of the sky. And the estimator can tell whether a region has been magnified or not, because if it's been magnified, that CMB power spectrum will be shifted to larger angular scales than the average power spectrum. Okay, so this modulation of our standard power spectrum, that's the signature we're looking for, and that allows us to go from a map of the CMB to a map of the gravitational lensing. All right, and here is one of these maps of CMB lensing. This is kind of a historical relic. I think the first one that we made back when I was in graduate school. You can see a small cutout of the sky, and the color scale tells you the strength of the lensing you have in certain directions. Now, mapping the lensing is really, really neat. It's really interesting because the strength of the lensing, or more precisely, the Laplacian of the lensing potential, is a direct gravitational probe of the density of mass and dark matter, right? So it's a probe of the overdensity projected over a wide range of redshifts, where for CMB lensing, we're getting signal from redshift around 2 and from very large scales. All right, as usual in cosmology, we don't do things by just staring at maps. We want to make this information quantitative. And the way we do this, as usual, is we measure a power spectrum. In this case, it's not the CMB power spectrum, but it's the lensing power spectrum CL55, so the power spectrum of this map. So the lensing power spectrum is shown here in this plot. It tells you the strength of the lensing as a function of the angular extent of the lens, right? So how much lensing do you have as a function of the size of the lens? The amplitude of the signal, as you might expect, since lensing probes projected mass, depends on sigma 8. So this lensing power spectrum CL55 depends on sigma 8. It's actually proportional to sigma 8 times the 4th root of the matter density. All right, so let's return to this original problem. What is going wrong with the growth of structure? And in particular, how can CMB lensing measurements with ACT that I'll talk about now contribute to this picture? So we will produce a new state-of-the-art precision measurement of the growth of structure. It's a 2% precision of S8 and sigma 8. And the nice thing about this, and the reason you might want to add another point to this long list, is that it's completely independent from anything else on here. So an ACT lensing measurement is independent of Planck, and it's certainly independent of all the potential systematics and galaxy surveys that you might worry about. So that's one reason you'd want to add this. Another reason, why you should want to add more points to this long list is if you think that what's going on here is really new physics. And the reason for that is that even though we map all of these measurements to one S8 parameter, they're really probing the growth of structure on different scales and at different redshifts. So this is an important plot. It's sort of schematic, showing you how different probes like CMB lensing power spectra and Lyman alpha and galaxy lensing, et cetera, probe the growth of cosmic structure on different redshifts and on different scales. And if you want to confirm and learn about new physics, this is really important because different types of new physics have signatures in their scale and redshift dependence. And that's why you need all kinds of different probes to confirm and learn more about any new physics affecting the growth of structure. Okay, let me turn now to our main results, our measurements of gravitational lensing with the Atacama Cosmology Telescope and what they mean for the growth of structure. So let me introduce briefly the Atacama Cosmology Telescope and the CMB data set that we're talking about. Up here you can see the ACT, or Atacama Cosmology Telescope. It's a 6-meter ground-based CMB telescope located very high up in the Atacama Desert, operates via many thousands of sensitive TES bolometers. It's actually a former telescope. This telescope was dismantled just last year, carted off the mountain because we're now deploying Simons Observatory, but there's some amazing data on disk that the ACT collaboration is now working to analyze and publish. All right, so let me show off one of our nice CMB maps. This CMB map is part of what I think is a really great data release from ACT, more or less the final one, ACT Data Release 6. So ACT Data Release 6, I think, will be a real milestone for ground-based CMB. And in short, that's because for the first time, the science and the parameters we're doing, in general, will really go beyond the Planck levels in precision. For lensing, this nice CMB map is great, more specifically because it has everything going for it. It covers 16,000 square degrees, almost half the sky. It has really high resolution, arc minute resolution, and very low noise. So it's 10 times more data than in the previous release. All right, so without further ado, let me just show one of our main results, which is a CMB lensing dark matter map that my group and our collaborators in ACT reconstructed from this CMB map. Okay, so this is one of our main results, the ACT DR6 CMB lensing mass map. So what's shown here in particular is the gravitational lensing convergence, the Laplacian of the lensing potential, which is directly proportional to the density of mass projected over a wide range of high redshifts. Okay, so this map has been filtered so that you're really seeing real structures. This isn't noise, this is real structure in the dark matter at redshift 2. Right, so the lighter the color is, the more dark matter you have in that direction. And it's also it's a pretty large map. This map covers a quarter of the sky at really nice fidelity. And I think it's just really cool that we're getting to the point now that we're able to map all the mass in the observable universe, at least over a significant fraction of the sky. All right, let me just show this map off a little bit more. I'm going to zoom in onto this small gray rectangle, show it a zoomed in version. And again, you can see these structures in the mass and the dark matter at redshift 2. And I claim that these are high fidelity, that you're really seeing real large scale structure in these images. Now, I could try to convince you of this by showing you various spectra, but there's a nice trick you can play so that I can show the fidelity of the map and that these are real blobs of dark matter. And that trick is to overplot the distribution of galaxies at similar redshifts, because we all know that the distribution of galaxies should follow the underlying dark matter that we're claiming to image here. So we can check that. Let's overplot on top of this lensing map a contour that shows us how much light we're receiving from galaxies at similar redshifts. So this is the cosmic infrared background observed at which is light coming from dusty galaxies at around redshift 2, overplotted on top of the same CMB lensing dark matter map. And hopefully you agree that the galaxies seem to follow the underlying dark matter. Now, I think no one should be surprised by this. We know that luminous objects should follow the dark matter, but first of all, it's nice to see this, and it's a nice illustration of the fidelity of our dark matter map. All right, let me turn now more, though, to quantitative cosmology, our lensing power spectrum measurement, and what it means for the growth of structure. And I should emphasize that a lot of the key work here and everything in my talk was led by great junior people, such as my former student, Frank True. All right, so we have a lensing map. We want to measure the lensing power spectrum and learn what it means about structure growth and tensions. In principle, that's pretty straightforward. It's not quite as easy as just, squaring the lensing map in harmonic space because there's some noise biases, but this is something we've been doing for many years. We know how to do this analysis and build this pipeline. What's much harder, given that we're pushing sort of to a new regime in ground-based CMB lensing, is being really sure that you believe your result at the percent level precision, right? Because this is getting really precise. Precision cosmology is hard. Fortunately, the DR6 data set has lots of redundancy that allows us to gain confidence in our measurement, allowing us to do more than 200 null tests in a blind analysis framework to make sure that we really believe our measurements of the growth of structure. So for example, we can check that we get the same lensing on different scales in different parts of the sky with different parts of our experiment and different frequencies and so on. Now, initially, getting into the details here a little bit, none of this worked particularly well. There were two challenges that we needed to overcome to make this measurement work at the precision that we needed. And those challenges are the sort of noise challenge and the foreground challenge. So let me talk about both of those very briefly before I show our results. The noise challenge was the fact that when we ran noise through our pipeline, if you run just noise through, you better get 0. But instead, we got this horrible failing green point, series of green points there. So what was going on? We realized soon that the ground-based noise due to things like the atmosphere was just so complicated that it was breaking the assumptions in our pipeline. And so we had to come up with a new way of measuring lensing that basically only used cross correlations between different parts of the data at different times. And in this way, we were able to completely zero the noise bias and solve this problem. So, taking our test from these horrible failing green points to everything looking nice as in blue. So that was the first challenge that we had to overcome. And the second challenge is the challenge of what I would call extragalactic foregrounds, even though other people would call them signal. And that is the fact that as the CMB photons travel to our telescopes, they're not just gravitationally lensed, but they're also joined by photons from galaxies and scattered by an effect named after someone in the first row here. And you can actually see the clusters and dusty galaxies in these CMB maps as these blue and red dots. Now, fortunately, as you can see here, this also doesn't look very much like lensing. So you can deal with these problems simply. The two options that we both applied are geometric mitigation, where we change the estimator so it doesn't pick up point-like sources, and a frequency-based mitigation, where we make use of the fact that things that are not the CMB don't have a blackbody distribution. So with multi-frequency data, you can separate. So both of these approaches worked really well. All right, and in the end, this null test suite looked great. And we found excellent consistency between the amplitude of lensing. So this is the amplitude of our lensing. We found the same lensing at different frequencies, in different parts of the sky, on different scales, in temperature versus polarization, and so on and so on. And so with that, then, we were ready to unblind our results and see whether our measurements agreed with the predictions or whether they were low, like so many other results. All right, so here, let me just sort of walk you through our unblinding. What's shown here is the sort of predicted CMB lensing power spectrum, CL5I, as I've said, based on an early time, fit to lambda CDM, extrapolated forward in time. This theory curve, we were never allowed to compare with our actual measurements until we unblinded. All right, so what happened is we got on a call, Frank decided we were ready to go, and we all decided that, and Frank pressed a button, and for the first time, we compared our CMB lensing power spectrum measurements in red with the sort of predicted curve based on early time CMB anisotropies in black. So, this is, again, one of our key results. And, I was really surprised that the agreement was so good, right? So these red points are just bang on the prediction, and they have a very good chi-squared. And, this is true at 2% precision. So, this is a big success for lambda CDM. And I emphasize again that this black curve is not a fit to these red data points. It is a prediction based on the early universe fits and assuming lambda CDM. And a lot of physics had to go right for this to work. Right? You fit your model to lambda CDM, you predict how structure grows over billions of years, you predict how this lenses the microwave background, you measure this lensing signal in a completely different experiment, and it works at 2%. So that's kind of amazing. All right, this agreement with prediction is also reflected in the cosmological parameter constraints that we obtain. So our constraints from ACT lensing alone are shown in this blue contour. Lensing, as I told you, constrains sigma 8, this amplitude of structure. It also has some dependence on the matter density. So our measurement corresponds to a parameter S8 of 0.818 plus or minus 0.022. This is, more or less state of the art. And now we can compare this with the prediction based on Planck and based on lambda CDM. That's this orange contour in the middle. So it's an excellent agreement. Our lensing doesn't appear to be low at all. We can make this statement even sharper and more precise by combining our CMB lensing measurements with some external data sets. We can add some the Planck lensing measurements. They make the constraints a little tighter. And we can add baryon acoustic oscillation data from galaxy surveys, which pins down the matter density omega matter. And that gives us probably our main result, this direct measurement that we get here in the sort of solid red contour in the middle. So this very precisely constrains sigma 8. We get a result of 0.812 plus or minus 0.013, and this is, to my knowledge, more or less as good as anything else that's out there. And I do really believe this result, given all the checks we've done. All right, how does this compare with the prediction? Well, that's this black contour in the middle. And the agreement, as you can see, is almost surprisingly good. So this is, I think, an important result, because this kind of agreement at this percent or so level really disfavors any new physics that significantly affects and messes up the growth of structure at early times, redshift greater than 1, and large scales. Right? So if you're building some new physics model, you have to deal with this level of agreement. All right. Does that mean that we're saying that all the other measurements are wrong that are finding tensions? We're certainly not saying that. It's worth bearing in mind that we can only make statements about the range of redshifts and scales that we've accessed, redshift 2 and large scales. It's possible that there's some real effect, some real new physics or new astrophysics that's kicking in on small scales or on low redshifts that we have not probed. One of these possibilities, the idea that maybe the S8 tension is kicking in, is some new physics that kicks in at very low redshifts, that's something that we can examine by using our CMB lensing measurements in a different way, namely by cross-correlating them with galaxy surveys at very low redshifts. All right, and this is again work led by my student Garrett Farren. The idea is we're gonna not just use galaxy surveys, because if we have galaxy surveys on their own in projection, they can't tell us about sigma 8 because there's a degeneracy with galaxy bias. Fortunately, we can add these CMB lensing galaxy cross correlations and break this bias sigma 8 degeneracy and solve for the growth of structure, now not at redshift 2, but at redshift 1 and 0.5 and so on. There are lots of ACT cross correlation projects with this lensing map that we're working on now. I'm going to talk about one that I think is particularly exciting, the correlation of our lensing map with the unwise galaxy sample, which you can see here. It's a great galaxy sample measured at micron wavelengths. It, huge number of galaxies, 150 million, over 30,000 square degrees of sky, and it covers an interesting redshift range. So it's not coming from redshift 2. It's now coming from redshift, 1.1 and 0.6. That's where the two samples, the green and the blue sample, lie. All right, so let's measure the cross spectrum and figure out what we learn about the growth of structure at low redshifts. Okay, let's correlate our lensing map with the galaxy distribution. And if you were not convinced by my contour plotting, hopefully you'll see that indeed we're correlated with the large scale structure from these cross spectra. We have two cross spectra, one with the blue sample at redshift 0.6, and one cross correlation with the green galaxy sample coming from redshift 1.1. All right, what do they mean for the growth of structure and for sigma 8 now at low redshifts? Well, fortunately or unfortunately, depending on your perspective, the agreement that we find continues to low redshift. So what we get from our low redshift constraints is 0.813 plus or minus 0.015 for sigma 8. So that's this black curve here. And you can compare that with the lambda CDM early time prediction. And again, it's in great agreement. So we find consistency with lambda CDM, not just at redshift 2, but also at redshift 0.6 to 1.1, at least on large scales. So maybe let me just summarize everything I have told you about the ACT measurements of the growth of structure so far in one plot. And this is a plot showing sigma 8 as a function of redshift. Okay, so growth of structure as a function of redshift. This plot is normalized by dividing by the standard lambda CDM sigma 8 of z, so that a value of 1 means everything matches standard structure growth. So I've talked to you about three measurements. In purple, the lensing power spectrum at redshift 2, and then the cross correlations with the green sample at redshift 1.1 and at 0.6 with the blue sample, and they all agree at sort of percent or 2 level precision, following the lambda CDM prediction. All right, now, what does that mean? Does that mean, again, now that we can say that everyone else has got it wrong? Well, certainly not. So all we can say is that in the range of redshifts and scales that we've probed, which are still large scales, but now extending over a pretty wide range of redshifts, from our perspective, lambda CDM standard cosmology seems fine. Now, there is an asterisk here, which is that I presented our results, and even in the same range of redshifts and scales, there's not full consistency. So there's some ACT results that are a little bit lower, and there's some other results that are, enormously lower. I'm happy to talk about those if you want. But, I think the main motivation for the tension were these galaxy lensing results, which are mostly coming from smaller scales. And we can't really say anything about those. It could be that there are systematics in one or many of these data sets, but it could also be that there's some scale-dependent suppression in the growth of structure that we're just not seeing. And this could either be due to astrophysics, like maybe we've underestimated the strength of baryonic feedback. Or, the most interesting possibility, it could be that there's some scale-dependent new physics, like some interesting dark matter phenomenology that's suppressing the growth of structure. So I think, which of these possibilities, whether it's sort of systematics or new astrophysics or new physics, is occurring here, I think is an interesting open question. And fortunately, we'll have measurements at increasingly high precision of the C and B lensing, but also of the gas with the SE effect, et cetera, that will help to clarify this picture further. So with that, I'll leave you with my summary, and thanks very much for your attention.
It's interesting insight, and I think there are some questions, and we can accept them. No, there is one.
I don't know if I have the slides. Sorry, could I have the slides
black
back?
and white one,
Yep.
the lensing map. By quick visual inspection, seems their size more or less similar by quick vision. But in principle, I guess you can infer those mass blobs, whatever the size and the mass. Is that correct?
So, the size of, right. So in part, the size of these blobs is set just by the peak of the lensing power spectrum.
Right.
Right. So that is a genuine physical feature, right? It comes from the matter
So I
radiation.
could
equality.
understand that as a kind of a mass reservoir. Would that be correct?
Yeah. So there's a sort of typical kind of mass scale, but there I have to qualify that the filtering does matter a little bit. You're cutting off some of the smaller scales because they're noise dominated, and we only want to show real structure.
But
right?
in principle, you could do the statistics to say what size, how many numbers, and smaller size and larger size. You could do that, right?
Yeah, exactly. I mean, in some sense, that's the lensing power spectrum sort of tells you that, right? Because you have, how, large are different, lenses of different sizes. But that's exactly what we can do now.
Hello, thank you very much for your talk. Very interesting. So can you put constraints or another cosmological models which have effect in the growth of the structure and the, for example, a cutoff in power spectrum, so for example, work dark matter or even action dark matter? Can you, perhaps in the particle mass, put constraints? Thank you.
Yeah, so I think we can, but we're not going to be the best at ruling out this kind of effect, right? So as I've mentioned, what we're really good at is sort of high redshifts and large scales. So if you want to rule out some early dark energy model or something like that, where the effects extend to large scales, this is a great probe, or neutrino physics or things like that. Things like, warm dark matter model where there's a cutoff at really small scales, maybe things like Lyman alpha would be, are giving perhaps more competitive constraints. Although certainly people look at axion constraints and things like that with CMB lensing, and it is, in some sense, it's a very nice and robust probe. You don't have to model much astrophysics. So I think there's still some value to these constraints as well.
One more question. Out of this, can you give some constraint on the bias factor? You mean luminous matter versus dark matter as function of scale?
Yes, we certainly can do that. So in fact, when we do the analysis, the cross-correlation analysis, if we want to get cosmology out of this, at the sort of percent level precision, we have to include not just linear bias, but we have a full sort of effective field theory model that has all of the different scale-dependent bias terms. And so, I can show you constraints on B2, BS squared, et cetera, that are present. So that's all in there.
So I think there's often a correlation between the S8 tension and the Hubble tension, in the sense that things that you'd think would alleviate the one would make the other one worse. And I think that's consistent with your comments on there being tight constraints, for example, in early dark energy. So if the Hubble tension is a real thing, what would be the implications of your work and your results for that?
Yeah, no, that's a very good question. I mean, I think, as you said, they make each other harder to solve. And so I think the proposals are that either you don't believe in one of the tensions, which one could advocate, I'm not maybe going to do that, but or you have to solve them with sort of separate mechanisms to some extent. I mean, from our results, we actually can make a measurement of H0 as well. I haven't had time to talk about this. And I think this measurement is also really cool because it doesn't depend on the sound horizon scale, right? Most CMB and large scale structure measurements, they have the standard rule that's the sound horizon scale. People come up with new physics ideas to mess with that. We have a different standard ruler, the peak of the matter power spectrum. And despite being different physics, we still get 65 or 66. So I think from our results, we shouldn't really necessarily, we're not really consistent with attention in that respect. So, but yeah, it's a hard problem if you want to solve both of them.
Thank you again. And before we come to the last speaker, again, I'd like to give the microphone to Remo, because
Yeah, I think while we are approaching 2 p.m., I think we can be connected with Chris Fryer, who's here. Oh, good. And proceed therefore. What time is now where you are?
It's 5:49, so 5:50.
Okay, therefore we are a little late on what planning, but we are very happy to be here and to conclude the ceremony of the award to you. And we had the ceremony this morning, starting with the Lee, which was very interesting, and one of Vicky Caspi for the team, and has been very, very beautiful ceremony, and we are a little pressed now because it's approaching 2 p.m. But of course, it is a great pleasure to give you to nominate for the award, and the reading is to Chris Lee Fryer, for his pioneering and groundbreaking theoretical and numerical simulation contributions that have advanced our understanding of supernovae, gamma-ray burst, and binary stellar evolution connecting them. And the award is just the test from the artist Pirelli. And of course, this is a celebration of this multi-year collaboration that we have had through the years. And we are very, very happy to for this award, which we will need to have an occasion, like traditionally we have the award given personally And also in this case, we will need to do that in the next occasion. And in fact, in this occasion, we are going to give another award in the past, which is the one that we had attributed during the period of the pandemic. But this one, therefore, this is your award, Chris, and we look forward for an occasion, maybe not possibly before the next Grossman meeting, to give the ceremony of giving you the award personally. But maybe I and with that, I think we have been running late on time. We will do a great celebration when we will meet together in the future. Okay, for the moment, just note that this has been awarded. Thank you very much.
Thank you very much, Remo. I'm very honored to get this award, and I'm glad to be here at least virtually, and I hope to be there physically before the end of the year.
Okay. We'll do best. We'll be at the next Grossman meeting, but we will welcome you at any moment soon after the break of the summer. Thanks.
Thank you.
Congratulations from my side as well. Please go on with your presentation now.
Okay, so I thought I would talk a little bit about I titled this "The Ever-Changing World of Astrophysical Transients," and what I really want to do is give a story on how much we've learned in the last essentially during my career, so over 30 years in astrophysical transients, how these advances have happened, and it kind of ties with some comments that I heard Ray Morfini say yesterday about the importance of how technology helps drive how our science progresses. So I'm just going to give a little overview of where, what kind of major changes in the last 30 years and kind of what are the open questions and what our future looks like in astrophysical transients. So let's start with supernova 1987A. This was when I was an undergraduate. A supernova went off. It was nearby in the Magellanic Clouds. There was a full set of theory models saying this has to happen from the collapse of massive stars. Supernova 1987A was the collapse of a massive star, so it bolstered our theory. But we also had some predictions that we did not see in the observations, and one of them was the arrival of the gamma rays. So what I have here is a plot of by Phil Pinto and Stan Woosley, where they had models of the gamma rays coming out of the explosion from supernova 1987A. The gamma rays were made from nickel 56, which is produced in the very inner region of the supernova engine. So it's right in the center where it's produced. You'd expect most of that nickel 56 to be in the center. And so if you went to observe it, you would expect to have to wait for it to get uncovered, because when the explosion first goes off, all that nickel 56 is down in the center, the rest of the stars on top of it. You wouldn't expect to see any observations. So the prediction was, well, it should start rising in about 250 days. It'll peak, 50 or 100 days later, and you'll have this strong gamma ray signal. What we ended up seeing was by 150 days, we already started seeing gamma ray emission. The emission was bright for nearly 500 days or even more. So we had this strong signal that we were not predicting. The solution that Pinto and Woosley had was somehow this nickel had to get mixed out. It had to not be close to that central engine, but it had to get mixed out. And this was the start of a lot of the theorists thinking of what new kind of engine could cause that kind of extensive mixing. And so a lot of models were predicted or produced. People studied both inhomogeneities in the star itself that would somehow drive mixing. But in the end, we kind of homed in on this convective engine model. Hrant et al. Did the first real calculations of this convective engine model in 1994. It was a lot of work by Mark Hrant and Willy Bands and Sterling Colgate studying convection right above the protoneutron star after the collapse and bounce of the protoneutron star. So it was this observation that drove us to coming up with a new theory to explain these explosions. So this next plot is I'm showing you a picture of that convective engine. This is a slice of a three-dimensional simulation where you see at the very center is the protoneutron star core. On the outer side, you see the star still collapsing in on itself. So this inner part of the core has collapsed in on itself, bounced, moved out, and then stalled. And you have this region where you have the protoneutron star on the inside, you have the material falling in on the outside, and the arrows here are the direction of the velocity and the magnitude of the velocity. So you have material falling in on itself. The color is entropy. And what you end up producing here is a very hot entropy material that wants to rise up and convect. And the material, as it falls in onto this convective region, starts to fall in and go in through downflows. So you have this kind of convective boiling that happens that we now believe is the explosion mechanism for it's the standard paradigm for most normal supernova. This convection will occur. You'll keep on getting energy, pulling it out of that protoneutron star as that energy leaks out in neutrinos. You'll deposit that energy into the convective region. It will convert that thermal energy from the deposition to kinetic energy to try to blow off the infalling star. And when it does blow off the star, you get an explosion. This has become the standard paradigm for what we think of are as new, the kind of, if you see a 10 to the 51 erg explosion, it's probably some kind of convective engine like this. The questions that we then wanted to do is say, okay, so you have this mechanism. What does that tell us about observations? Is there some way to prove that this kind of convective engine could be the right answer? So we had observations that told us we're missing something, so we had to look more deeply. One of the other points that I wanted to make out, and that's the picture on the upper right. The other thing that led to our advances is better. It's not just better technology for the detectors and better observations, but it's also better technology for the theory, which comes in better computing. And about the era of we were doing these simulations in 2002, we were also developing a new kind of computer, which was, let's take the commodity parts that are being developed by industry and connect them together. This is, and the initial kind of doing this commodity computing was called Beowulf computing. And up in the right corner is an early Beowulf computer. It's called the Space Simulator. It was made just by taking a whole bunch of little shuttle boxes off the shelf. They were tiny computers that they sold for people to work in their offices, fit on their desk. We connected them all together and built the 75th fastest machine in the world just by using these commodity parts. Now, when you think of a supercomputer, you actually are thinking of a commodity computing, one of these Beowulf clusters. It's the standard high-performance computing supercomputer that we use today. So, but it was at the time in its infancy, and it's that technology development that actually led to these advances in our understanding of core collapse supernova. So we're going to now take these and try to predict, see what we can predict for observations. So one of the things that one could study is go back to those gamma ray lines. So we had seen the gamma rays that arrived early. The other weird feature about the gamma rays was that they were redshifted. So if you were thinking of you have a nice spherical explosion, you would see the gamma rays first coming at you. So they'd be blue. The line features from the gamma rays from this nickel 56 decay would be blue shifted, and you'd expect some blue shifted features. Instead, we saw features that were red shifted. So what that actually meant, and this image is showing, is here's in the middle plot here is a slice of a 3D explosion where we assumed the explosion was asymmetric, going off in one direction, and that material was moving off and if it was moving away directly away from us, it would take some time to see it because we have to see through the whole star, but you would see very redshifted lines. That's not what we saw. We saw the gamma rays early, but if you took that same material, mixed it out, and drove it out in a kind of a 45-degree angle, the image on the top right, you'd get a redshifted feature of this material moving away from you, but you would actually see you would get an observation of a redshifted feature. So we were able to explain this kind of, if this convection went to low modes, you could get a redshifted feature. So this was the kind of first test of this convective engine. Can it explain the gamma rays that we saw? It seemed to fit the data. But we just still didn't have, this was kind of, the data was pretty sparse. You always want some kind of confirmation beyond just this looks like it fits the generic picture that we have. And this confirmation happened with the observation of titanium-44 in the supernova remnant Cassiopeia A. This is an image that includes both the Chandra observations and new star observations of the Cassiopeia A supernova remnant. The green is a silicon feature, the red is an iron feature, and the cyan color is the titanium-44. Titanium-44, like nickel 56, is made in the very center of the explosion. So it is a direct tracer of the explosive engine. Without that observation, when we looked at the Cassiopeia remnant in Chandra in the X-rays, we had this green feature that really looked like maybe this was a jet-like explosion, so not so well fitting the kind of convective engine that we see. And so the prediction was, or the comment was when these observations first came out is, oh, well, it's not a convective engine, it's this jet-like explosion. It was weird because the iron that we were seeing was off in a different direction. It was not in the same direction as the silicon. And it was also weird in the sense that we were quite limited in what we can see, because when you're looking at the silicon or the iron features, you're looking at only that material that is shock heated. So the reverse shock had to come back and heat the material. And all of that material, it's hard to, disentangle that the actual ejected material, the material from the star itself and its surroundings. So that was never, on the theory point of view, we never really believed that this necessarily said that you had to have a jet explosion. But we figured if we can go see it in titanium-44, which is a clean observation of the explosion mechanism, if it were a jet-like feature, we would see the titanium in that same jet-like feature. And that's not what we saw. We saw a clumpy titanium feature that was more indicative of a asymmetric explosion mechanism. So this was a situation where the observations initially told the theorists, you're wrong, it cannot, this convective engine doesn't work, to maybe this is exactly what is going on. It is a convective engine. The exciting thing here is we're still getting more data. So Milosavljevic has some recent results using JWST to observe a full suite of different elements. The advantage of the infrared is you can see material that even if it's not shock heated. So this is we're still trying to disentangle this event. We still don't really understand the silicon feature that we see. So there's a lot of new discoveries that are still happening with this. But at this point, we're pretty secure with Cassay's telling us that this kind of convective picture we have is correct. We could take this in some steps forward. So I've already gone through two different observations that have led us to get a picture of what the supernova engine is. We looked at supernova nickel 56 decay during the explosion itself, and then we looked at an aging remnant, so the ejector remnant as it moves out. But you can also look at the compact remnants that supernova produce. And the way I have these arrows going, I'm going from the theory to all the way to the observations. The theory is we can study this convective engine. We can study how quickly it grows, how strong the growth of the convection is, and we can make our models aren't perfect yet. So you can't take a theoretical model right now and say, this is the quantitative answer. In fact, that may not happen even in my lifetime. Getting enough resolution in our theoretical models in 3D so that we actually are getting we're not overestimating the numerical viscosity and getting the right convective growth time might be beyond what we can do computationally. But we can say we understand this physics. We can study, we know it's the growth of this convection that matters. We can play with that growth time. And that's what I did in this left figure, where I have the CO core mass and the remnant mass in a series of different curves. Those different curves are me playing with the growth time, trying different values for the growth time, seeing what kind of remnant happens if the convection grows at different time periods, and then looking at that, plugging that into. We have to plug that into some extra data. I have to plug that into binary population synthesis models, and then ask the question, how does that change what the mass distribution of neutron stars and black holes are? And what we found is this mass gap that we've had between about 2 and 5 solar masses or 2 and 4 solar masses, depending on your observations. That mass gap between neutron star and black hole masses can get filled in depending on how quickly that growth time is. So the different colors here are for different growth times, and as we alter the growth time of the convection, we fill in that mass gap. So then the exciting thing is, can we observe that mass gap? And one of the exciting potential for gravitational waves is enough observations where we can get a really pristine mass distribution of compact remnants. And so here's the mass distribution from the LIGO collaboration in 2021, going from 1 to 2.4 solar masses. And you can see the masses and how they fill in, and they're slowly getting an idea of what the mass distribution of neutron stars and black holes are. So this is another observation that is going to get us at understanding the engine behind core collapse supernova. But there's a whole suite of constraints that we can get in supernova. They range from, if we have a galactic supernova, we'll get gravitational waves and neutrinos, MeV neutrinos. I talked about compact remnant masses. There's a lot of work now being done at looking at, we have a lot of data in the optical of the supernova and the light curves. And one of the things we're realizing is we don't really know the environments around these supernovae as well as we thought. If we get those environments more nailed down, that'll help us analyze the Cassay remnants like Cassay better, so the ejector remnants better, because we'll understand what are the circumstellar medium around these stars when they explode. We can study the nucleosynthetic yields. We can use measurements like polarization to try to get a better idea on the asymmetries. And also, if we look at polarization of the remnants, we can study magnetic field distribution. So there's a lot of observations that we keep on adding and kind of go to work together to get us a good understanding of the supernova engine. And as we get a better understanding of the supernova engine, we can also probe the physics behind it, the dense nuclear matter, the neutrino physics that help drive the explosion. So this is one of the exciting things that I think is happening in in astrophysical transients is we're really taking advantage of all the diagnostics we can apply to doing these studies. And when you're trying to do this kind of precision science, it was discussed just in our previous talk, you really need to somehow you need redundant data to try to give you an idea of what's really going on. And I think that's the kind of the exciting potential for core collapse supernova. I wanted to end my last 5-6 minutes on a little discussion on gamma ray bursts and how they've altered as well. So I'm starting here in 1997, so 10 years after what I started for my history of supernova, and the observations of absorption lines and gamma ray bursts. So pre this period, there was growing evidence that gamma ray bursts had to happen outside of the galaxy. So, but we had just come through this the great debate where we had the Paczynski versus Don Lamb arguing about whether gamma ray bursts were galactic or extragalactic. And I will tell you from a lot of the theorists that I knew, we wanted it to be galactic because the energy requirements for extragalactic gamma ray bursts, as we all know, were immense. And so it was pushing what we could do to get energetics if they really were extragalactic. But the observational evidence was pushing us that it had to go extragalactic, and the GRB 970508 really drove it home, where there was no way around it. We saw absorption lines, we could get their redshift. We knew that these objects were extragalactic. And at these distances, then the explosion energies had to be really energetic. And that started to kill off a lot of our engine models for gamma ray bursts, but at the same time, it started to make them more detailed and allow us to do a whole new level of physics when we studied engine models. And so we still have a set today that we argue about. There's the black hole accretion disk models, the so-called bad GRB models. There's magnetars. You can maybe do gamma ray bursts from neutron star accretion disks in a similar engine style as the black hole accretion disk. And then there's also the induced gravitational collapse models where you tie it together with binary driven hypernova for the progenitor. And there'll be more talks about that in one of the parallel sessions today. So we have those different engines. We also have to come up with what's the progenitor for these engines. And the hardest part with these, the progenitor was coming up with the angular momentum. A lot of the models, black hole accretion disk, neutron star accretion disk, magnetar, all require extremely fast rotations to explain their engines. And it's probably why these are rare events. We don't see one of the reasons why it's unlikely that Cas-A has a jet in it as well is it's just hard to get enough angular momentum to produce such engines. But a whole bunch of progenitors have been proposed. Here's a table of different progenitors that were being studied. You can have rotating stars, so it's just a single star. It's really hard to get a rotating star rotating rapidly enough to make a magnetar, neutron star accretion disk engine to work. You might be able to get a black hole accretion disk engine to work if you have very weak ties between the different burning layers in the stellar evolution. So it's a stellar evolution question of how does the burning work in these stars. I'm not going to go through all the models, just a wide set of models that people have proposed. One of the exciting things is the argument was, well, things like massive stars that were somehow rotating would explain the long duration gamma ray bursts, and the things like neutron star mergers, neutron star merger, neutron star black hole mergers would explain the short duration gamma ray bursts. So there's a dividing line in which progenitors explain which bursts, and they actually made predictions for what you would see in the things like the offsets of these bursts. The argument that was that if you were forming short bursts from mergers, they would be kicking. They would get kicked, and they would move further out from their host galaxies. And the long bursts would be more focused in the strongest star forming regions. And in 2013, Fungenberger did a really nice study where they had a lot of observations of neutron star, short duration gamma ray bursts, and they matched this neutron star merger scenario for gamma ray bursts. So we have some idea that our range of parameters are roughly correct. That doesn't solve a lot of the questions that we're still confused about for progenitors for gamma ray bursts. One of the, one of the observations that we're really struggling with is the fact that when we see long duration gamma ray bursts, we typically see, if we see some kind of transient along with it, it is a type 1c supernova, which means it doesn't have hydrogen, it doesn't have helium. So whatever that tells us about the progenitor, we somehow have to remove the hydrogen and helium to make it work. I'll point out that for the binary driven hypernova model with that's supported by Remo Ruffini and his team, that naturally explains why it can only form if it is a carbon oxygen core when you have the explosion. For these other models, magnetar, neutron star accretion disk, black hole accretion disk, whatever our progenitor is, whatever is making the fast rotations that we need to make these jets, must be something that ejects both the hydrogen and helium in quite a few of our cases. And so for these long duration gamma ray bursts, we still have a lot more work to do. There's a lot more questions. And I just want to say, I'm going to stop with, these are my last two slides. The exciting thing is we've made a lot of progress in the last 30 years, but we have a lot of open questions. On the right here is a plot of the nucleosynthetic yields for a particular supernova remnant W49b. And the dots are different stellar explosion models. This one is in case some of the models from Ken Nemoto's team. And the bars are the error bars on the observations of those abundances. And we're not getting the abundances right. So we still don't get the explosive abundances right. Samar Safi-Harb and her team have compared to a lot of different explosion models. None of them are getting the right supernova yields. So we don't know the yields yet. We don't know really what's doing powering all the observed emission. And we still have a lot of work to go if we want to use these supernova to probe things like neutrinos and matter in the extremes. In the same way with long duration gamma ray bursts, we don't know how we get the angular momentum. We don't really know what's powering these jets. And we don't know the progenitors. So there's lots of open questions. And I'll end with the fact that so there's a lot of open questions, but we have a lot of tools that are going to push us to make new discoveries. And I think we're entering a new era in astronomy where we're not just relying on observatories that are observing those astronomy events, but we're also, we can leverage a lot of laboratory experiments to help us better understand the physics. As we get to more and more precision astronomy, we need not only better observations and more accurate observations, both ground-based and space-based, but we're going to start probing physics and pushing physics to their limits. So, and it's not just nuclear physics, particle physics, but also things like how do we do radiation physics, atomic physics. We're pushing all of those right now in astronomy, and I think we'll take advantage of all of those tools and all of that technology development. And I'm throwing in there computing tools, going from everything from what we do now that was spawned from Beowulf clusters to commodity computing to faster GPU machines to even quantum computing. And so I think the future is bright as the technology keeps on building. We'll have a lot of discoveries. And I'll stop there.
Thank you. Thank you very much. Remo has a comment.
Well, thank you. Lots of things to do. We will keep going until the next Grossman meeting and further develop all this work. Thank you very much. And I thank all of you for the moment. We give the Dili, Caspi, now you have the one, and we will wait for all this beautiful clarification for the next meeting to deliver.